As we cast our gaze toward the future of space exploration, we find ourselves at a thrilling and transformative intersection, a place where the exponential growth of artificial intelligence meets the vast, silent, and often bewildering expanse of the cosmos. One of the most profound and immediate impacts of this convergence is the revolution it is bringing to our search for life beyond Earth. For decades, the hunt for exoplanets, worlds orbiting other stars, has been a painstaking process, a search for the proverbial needle in a cosmic haystack. But AI, with its insatiable appetite for data and its uncanny ability to recognize subtle patterns, is changing the game. AI algorithms can now sift through the immense data sets generated by telescopes like Kepler and TESS, analyzing the light curves of millions of stars with a speed and an accuracy that far surpasses human capabilities. They can detect the tiny, periodic dips in starlight that signal the transit of an orbiting planet, and they can even begin to tease out the faint, chemical fingerprints in the starlight that has filtered through a planet's atmosphere, searching for the telltale biosignatures of life. This is not just about accelerating the pace of discovery. It is about refining our focus, about allowing us to triage the vast number of candidate worlds and to concentrate our precious observational resources on the most promising targets, the worlds that have the greatest potential for harboring life. But AI's role is not just to analyze the data, it is also to help us get there. The challenges of navigating a spacecraft through the complex and often hazardous environment of deep space are immense. The communication delays, which can stretch to hours, make real-time, human-in-the-loop control an impossibility. This is where autonomous navigation, powered by AI, becomes essential. Imagine a spacecraft on its long journey to Jupiter's icy moon, Europa. It is equipped with an AI system that is constantly analyzing its trajectory, its position relative to the planets and their moons, the subtle gravitational nudges from the Sun and the other bodies in the solar system. It can make its own, instantaneous course corrections, optimizing its path to save fuel, to avoid a newly detected debris field, or to take advantage of a gravitational assist. It can even make its own autonomous decisions about which scientific targets to observe based on the real-time data it is collecting. This is not science fiction. It is the future of robotic exploration. A future where our spacecraft are not just passive, pre-programmed machines, but are intelligent, adaptive, and truly autonomous explorers, our robotic proxies in the far reaches of the solar system. The reach of artificial intelligence extends beyond the journey to other worlds and onto their very surfaces. The prospect of conducting complex in situ scientific research on a place like Mars, with its harsh environment and its significant communication delay, is a formidable challenge for human explorers. But for a new generation of intelligent, AI-powered robotic scientists, it is a world of opportunity. Imagine a fleet of robotic rovers, landers, and drones, all working together as a collaborative, scientific team on the surface of Mars. They are equipped with advanced machine learning algorithms that allow them to not just follow a pre-planned set of instructions, but to learn, to adapt, and to make their own scientifically driven decisions. A rover, for example, could analyze the geological context of a particular rock outcrop with its cameras and its spectrometers, and then, based on its onboard, AI-powered geological knowledge base, it could decide that this is a particularly promising target for a detailed chemical analysis, or for the collection of a sample to be returned to Earth. These robotic systems could work tirelessly, 24/7, conducting a systematic and comprehensive survey of the Martian environment, searching for signs of past or present life, and building a detailed, multi-layered picture of the planet's history. They would be our scientific vanguard, our partners in exploration, doing the dangerous, the repetitive, and the time-consuming work, and freeing up the human explorers when they eventually arrive to focus on the more complex, the more creative, and the more uniquely human tasks of synthesis, of interpretation, and of discovery. The design of the very spacecraft that will carry us on these journeys is also being revolutionized by AI. The process of designing a vehicle that can withstand the extreme stresses of launch, the vacuum of space, the high-energy radiation, the micrometeoroid impacts, is an incredibly complex, multivariable optimization problem. AI, particularly in the form of generative design algorithms, can explore a vast multidimensional design space far more quickly and comprehensively than a human engineer ever could. By feeding the AI the fundamental constraints of the problem, the required structural strength, the mass limitations, the thermal properties, the algorithm can generate thousands or even millions of potential design solutions, often coming up with novel, counterintuitive, and highly efficient structures that a human designer might never have conceived of. This is a new and powerful form of human-AI collaboration, a partnership that can lead to spacecraft that are not just stronger and safer, but also lighter, more efficient, and cheaper to build and to fly. The invisible, and often fragile, threads of communication that connect our deep space explorers to their home planet are another area where artificial intelligence is set to have a profound impact. As we venture further into the solar system, the challenges of maintaining a reliable and efficient communication link become increasingly difficult. The signals become weaker, the data rates become lower, and the potential for disruption from solar flares and other forms of space weather increases. AI can play a crucial role in managing this complex and life-critical communication network. AI algorithms can be used to optimize the scheduling of data transmissions, to dynamically allocate the limited bandwidth of the deep space network, and to prioritize the most important and time-sensitive data. It can also be used to predict and to mitigate the effects of space weather. By analyzing the data from a fleet of solar-observing satellites, a machine learning system could learn to recognize the precursor signatures of a solar flare, providing a few hours of advance warning to a Mars-bound crew, giving them time to take shelter in a heavily shielded part of their spacecraft. And AI's role in analyzing the vast and ever-growing archives of astronomical data is a revolution in itself. The new generation of survey telescopes, like the Vera-C Rubin Observatory, will generate more data in a single night than has been collected in the entire history of astronomy. It is a torrent of information that is simply impossible for human beings to analyze manually. AI, with its ability to sift through this data, to classify objects, to identify anomalies, and to find the subtle, hidden patterns, is the essential tool that will allow us to turn this flood of data into a new and deeper understanding of the cosmos. It is a new kind of science, a science where the process of discovery is a collaborative dance between the intuitive, hypothesis-driven insights of the human mind and the brute force, pattern recognition power of the artificial one. The future of space exploration is a future of partnership, a future where human and artificial intelligence work together in a deep and synergistic way to push the boundaries of our knowledge and to expand our presence in the universe. Our understanding of the cosmos has been a long and winding journey, a story of evolving perspectives that has been shaped by the interplay of culture, of philosophy, and of scientific discovery. The journey began with our most ancient ancestors, who looked up at the night sky with a sense of wonder and of awe, and who saw in the celestial dance of the stars and the planets a reflection of their own terrestrial world. The Babylonians and the Egyptians were meticulous observers, a people of the sky. They charted the constellations, they tracked the movements of the planets, and they developed sophisticated calendars that were intimately tied to the rhythms of the heavens. Their astronomy was a practical one, a tool for agriculture, for navigation, for divination. But in their careful and often beautiful records, inscribed on clay tablets and on the walls of their temples, they laid the foundational, empirical groundwork upon which all of Western astronomy would be built. The classical era of the ancient Greeks marked a profound shift, a move from a purely observational and mythological understanding of the cosmos to a more philosophical and geometrical one. It was the birth of cosmology as a rational inquiry. Aristotle, with his powerful intellect and his systematic approach, constructed a geocentric model of the universe, a beautiful nested system of celestial spheres with the Earth at its center that would dominate Western thought for almost 2,000 years. Ptolemy, in the 2nd century AD, refined this model, adding a complex and ingenious system of epicycles and deference to account for the observed, and often puzzling, retrograde motions of the planets. It was a model of immense mathematical elegance and predictive power, and it represented the pinnacle of ancient astronomical science. The Renaissance was a time of profound intellectual and cultural upheaval, and it was in this fertile ground that the seeds of the scientific revolution were sown. Nicholas Copernicus, a Polish canon and astronomer, was the quiet revolutionary who, in his book De Revolutionibus Orbium Coelestium, dared to challenge the millennia-old geocentric orthodoxy. He proposed a heliocentric model, with the Sun at the center of the solar system and the Earth relegated to the status of just another planet. It was an idea of profound and, for many, deeply unsettling implications. It was an idea that was given its definitive, observational confirmation by the work of Galileo Galilei. When Galileo turned his newly constructed telescope to the heavens in the early 17th century, he saw things that no human being had ever seen before. He saw the mountains and the craters on the moon, proving that it was not a perfect celestial sphere, but a world, much like our own. He saw the phases of Venus, a phenomenon that was impossible to explain in the Ptolemaic model, but was a natural consequence of the Copernican one. And most famously, he saw the 4 large moons orbiting the planet Jupiter, a miniature solar system that provided a stunning visual proof that not everything in the universe revolved around the Earth. Galileo's observations were a direct and powerful challenge to the established Aristotelian worldview, and they helped to usher in a new era of empirical, observation-based science. Johannes Kepler, a contemporary of Galileo, provided the crucial mathematical next step. Through a painstaking analysis of the meticulous observational data of his predecessor, Tycho Brahe, Kepler discovered his 3 laws of planetary motion, showing that the planets do not move in perfect circles, as Copernicus had believed, but in elliptical orbits, with the Sun at one focus. And it was the great Isaac Newton who, in the late 17th century, provided the final unifying synthesis. His law of universal gravitation provided a single, elegant, and powerful mathematical framework that could explain not just the motions of the planets in our solar system, but the fall of an apple from a tree. Newton's vision of a clockwork universe, governed by a small set of universal mathematical laws, would become the dominant paradigm of science for the next 200 years. The 20th century was a time of 2 great revolutions in physics, revolutions that once again, and in an even more profound way, transformed our understanding of the cosmos. The first was Einstein's theory of relativity, which did away with Newton's absolute space and time and replaced it with a dynamic, 4-dimensional space-time that could be bent and warped by the presence of matter and energy. The second was the birth of quantum mechanics, which revealed the strange, probabilistic, and often paradoxical nature of the subatomic world. These 2 revolutions, combined with the development of ever more powerful telescopes, led to the birth of modern physical cosmology. In the 1920s, the American astronomer Edwin Hubble, using the new 100-inch Hooker telescope on Mount Wilson, made 2 of the most important discoveries in the history of science. First, he proved that the spiral nebulae which had long been a source of debate, were not clouds of gas within our own Milky Way, but were, in fact, distant island universes, vast galaxies in their own right, each containing billions of stars. This single discovery expanded the known universe by an almost unimaginable factor. But Hubble's second discovery was even more profound. By analyzing the light from these distant galaxies, he found that, with very few exceptions, they were all moving away from us. And the further away a galaxy was, the faster it was receding. The universe was not static. It was expanding. This observation, now known as Hubble's law, was the first direct observational evidence for the Big Bang theory. The idea that the universe had originated from a single, hot, dense point in the distant past and has been expanding and cooling ever since. This theory, which was initially met with a great deal of skepticism, has, in the decades since, been confirmed by a wealth of observational evidence, from the abundances of the light elements to the discovery of the cosmic microwave background radiation. The latter half of the 20th century was the era of the space race, a time when the geopolitical rivalry between the United States and the Soviet Union fueled an unprecedented period of technological development and of exploration. The launch of Sputnik in 1957, the first human in space in 1961, the iconic Apollo missions to the moon, these were not just technological triumphs. They were cultural moments that captured the imagination of the world and that forever changed our relationship with the cosmos. We were no longer just passive observers of the heavens. We were active participants. A species that had taken its first tentative steps into the vast cosmic ocean. This journey of understanding, from the first naked-eye observations of our ancient ancestors to the sophisticated AI-powered explorations of the 21st century, is a testament to the enduring power of human curiosity. It is a story of courage, of ingenuity, of a relentless and often defiant quest to understand our place in the grand and ever-unfolding story of the universe. The story of artificial intelligence in space exploration did not begin with the sophisticated machine learning algorithms of the 21st century. Its roots can be traced back to the very dawn of the space age, to the pioneering missions of the 1960s and 70s, a time when the seeds of AI were being sown in the fertile ground of necessity. The Apollo program, with its audacious goal of sending humans to the moon, was a crucible of technological innovation, and at its heart was a small but revolutionary piece of hardware, the Apollo guidance computer. This was one of the first computers to use integrated circuits, and it was a marvel of miniaturization for its time, but its true significance lay in its software. The AGC was programmed with a rudimentary but highly effective form of AI, a set of algorithms that could assist the astronauts in the complex and life-critical task of navigating their spacecraft to the moon and back. It could process data from the inertial measurement unit, from the star tracker, from the radar, and it could provide the crew with real-time guidance, calculating their trajectory, controlling the engine burns, and even assisting with the landing on the lunar surface. It was a true human-computer partnership, a system that could manage the immense complexity of the mission, reducing the cognitive load on the astronauts and allowing them to focus on the most critical decision-making tasks. The AGC was a powerful demonstration of the potential for AI to enhance human capabilities in a high-stakes operational environment. The early robotic missions to the planets also relied on a form of proto-AI. The Mariner missions to Mars and Venus in the 1960s were equipped with simple, on-board automated systems that could execute a pre-programmed sequence of commands, taking pictures, collecting data, and transmitting it back to Earth. The ability to process and to prioritize this data was limited, but these missions laid the crucial foundational groundwork for the more advanced autonomous systems that would follow. The Voyager probes, launched in 1977 on their grand tour of the outer solar system, represented a significant step forward in this regard. Because of the immense distances involved, the communication delay with Earth could be hours long. Real-time control was an impossibility. And so, the Voyager spacecraft were designed with a much higher degree of onboard intelligence. They had fault protection algorithms that could autonomously detect and respond to a wide range of potential system failures. They had sophisticated onboard sequencing capabilities that allowed them to execute a complex series of scientific observations without constant input from the ground. They were, in a sense, the first truly autonomous deep space explorers. The Viking missions to Mars in the late 1970s took this a step further. The two Viking landers were the first spacecraft to successfully operate on the surface of another planet, and they were equipped with a robotic arm and a suite of sophisticated instruments for analyzing the Martian soil. The process of sample acquisition and analysis was largely automated, with the onboard computer controlling the movements of the arm and the operation of the scientific instruments. This was one of the first instances where AI was used to conduct a complex scientific investigation on another world, a precursor to the much more advanced AI-powered science that is being performed by rovers like Curiosity and Perseverance today. The early uses of AI in space exploration were born of necessity. They were solutions to the fundamental challenges of distance, of complexity, and of the need for reliability in an unforgiving environment. They were often rudimentary by today's standards, but they were a powerful proof of concept. They demonstrated the immense potential for intelligent, automated systems to extend our reach, to enhance our capabilities, and to allow us to explore the cosmos in ways that would be simply impossible with human operators alone. They were the first, tentative, but crucial steps on a journey that is now leading us towards a future of true human-AI partnership in the exploration of the universe. The parallel evolution of artificial intelligence and space technology in the latter half of the 20th century is a story of a deep and synergistic relationship, a feedback loop where the demands of one field have often spurred the innovations of the other. The dawn of the space age in the 1950s and 60s coincided with the birth of the digital computer. The immense computational challenges of spaceflight, of calculating orbital trajectories, of modeling rocket propulsion, of processing telemetry data, were a powerful driver for the development of the first large-scale mainframe computers. Machines like the IBM 7190 were the unsung heroes of the Mercury, Gemini, and Apollo programs, performing the millions of calculations that were necessary to send the first humans into orbit and to the moon. This need for precise real-time computation also led to the development of new, more sophisticated, and more reliable software algorithms, the foundational building blocks of what we would now call artificial intelligence. The Apollo guidance computer, as we have seen, was a milestone in this regard, a demonstration of how a compact, and by today's standards, incredibly primitive computer could be programmed with a form of intelligence that could safely guide a crew of human beings on the most complex journey ever undertaken. The 1970s and 80s was the era of the first great robotic voyages of discovery. The Pioneer, Viking, and Voyager missions, these missions, which ventured to the far reaches of our solar system, presented a new set of challenges. The immense distances and the resulting communication delays made real-time, ground-based control an impossibility. The spacecraft had to be given a much higher degree of onboard intelligence and autonomy. This spurred the development of the first rudimentary, AI-powered, autonomous systems capable of fault detection, of onboard sequencing, and of a limited form of decision-making. This was also the era when the first expert systems began to be used in mission planning and in the analysis of the vast amounts of scientific data that these missions were sending back. These expert systems were a form of AI that attempted to capture the knowledge and the decision-making rules of a human expert in a particular domain, allowing a computer to provide intelligent advice and analysis. The 1990s was a decade of profound transformation, both in space and in AI. The launch of the Hubble Space Telescope in 1990 opened up a new, breathtakingly beautiful, and data-rich window onto the universe. The sheer volume and complexity of the images and the data that Hubble produced created a new challenge: how to process, to analyze, and to make sense of it all. This was a problem that was perfectly suited to the newly emerging techniques of machine learning algorithms, which can learn to recognize patterns in data without being explicitly programmed, began to be used to automate the process of classifying galaxies, of identifying stars, and of searching for transient events in the Hubble data. This was the beginning of the transition from a world where AI was used primarily for control and for automation, to a world where it is also used for scientific discovery itself. The development of neural networks, a type of machine learning algorithm that is loosely inspired by the structure of the human brain, was a key breakthrough in this regard. These networks, with their ability to learn complex, nonlinear patterns, would later become the foundation for the deep learning revolution of the 21st century. The story of AI and space in the 20th century is a story of a co-evolving partnership, a story where the challenges of exploring the cosmos have consistently pushed the boundaries of our computational technologies, and where the new capabilities of those technologies have, in turn, opened up new frontiers for our exploration of the cosmos. It is a story that has laid the foundation for the current era, an era where AI is not just a tool for space exploration, but is becoming an indispensable and intelligent partner in our quest to understand the universe. The history of space exploration is punctuated by a series of pivotal, trailblazing missions. Missions that have not only expanded our knowledge of the cosmos, but have also served as crucial stepping stones in the development and the integration of artificial intelligence into our exploratory endeavors. The Voyager program, launched in 1977, is a prime example. The twin Voyager 1 and 2 spacecraft were sent on a grand tour of the outer planets, a once-in-a-lifetime alignment that allowed them to use the gravity of one planet to slingshot themselves onto the next. Because of the immense distances involved and the hours-long communication delays, the Voyager spacecraft were designed with a significant degree of onboard autonomy. Their fault protection software was a form of rudimentary AI, a set of pre-programmed rules that allowed the spacecraft to autonomously detect and respond to a wide range of potential problems, from a malfunctioning sensor to a loss of attitude control. This ability to self-diagnose and to self-heal was essential for the long, lonely, and multi-decade journey of the Voyager probes, a journey that has now taken them beyond the heliosphere and into the uncharted territory of interstellar space. The Mars Pathfinder mission, which landed on the Red Planet in 1997, was another major milestone. The mission's tiny, six-wheeled rover, named Sojourner, was the first robotic vehicle to operate on the surface of another planet. Sojourner was not a fully autonomous robot. It was largely teleoperated from Earth, but it did have a limited onboard AI capability. It could use its laser-based hazard avoidance system to detect and to navigate around obstacles in its immediate path, a crucial skill for a small rover on a rocky alien terrain. Sojourner's successful 90-day mission was a powerful proof of concept for the idea of using mobile, robotic explorers on other worlds, and it paved the way for the much larger, more capable, and more intelligent Mars rovers that would follow. The European Space Agency's Rosetta mission, launched in 2004, was a mission of breathtaking ambition and complexity. Its goal was to rendezvous with, to orbit, and to land a small probe on the surface of a comet. The challenges of navigating in the weak and unpredictable gravitational field of a small, outgassing comet were immense. Rosetta's navigation system used a sophisticated form of AI, a set of algorithms that could process the images from its onboard cameras to autonomously determine its position and its velocity relative to the comet's nucleus. This optical navigation was essential for the precise and delicate maneuvers that were required to stay in orbit and to deploy the Philae lander. The landing itself was a moment of high drama and a powerful demonstration of the need for onboard, autonomous decision-making in a time-critical and highly uncertain environment. The more recent Mars rover missions, Curiosity, which landed in 2012, and Perseverance, which arrived in 2021, represent the current state-of-the-art in the use of AI for planetary exploration. These car-sized, nuclear-powered mobile science laboratories are equipped with a sophisticated suite of AI algorithms that give them an unprecedented degree of autonomy. Their AutoNav system allows them to autonomously drive for hundreds of meters at a time, analyzing the stereo images from their navigation cameras to build a 3D map of the surrounding terrain, to identify hazards, and to plot a safe path forward. They can also autonomously select their own scientific targets. The Aegis system on Curiosity and Perseverance can analyze the images from the rover's mast camera, identify rocks that have interesting colors, shapes, or textures, and then autonomously fire the rover's laser-zapping ChemCam instrument to determine their chemical composition. This allows the rover to do a first-pass scientific survey of its surroundings and to flag the most interesting targets for the science team on Earth to follow up on. These missions, and others like them, are not just about sending robots to other worlds. They are about sending intelligent, robotic proxies, extensions of our own, human senses and our own. Human scientific curiosity. They are the pioneers of a new era of exploration. An era where the synergy between human and artificial intelligence is allowing us to explore the cosmos in ways that are more efficient, more capable, and more profound than ever before. The legacy of the Apollo program, the monumental achievement of sending the first humans to the moon, extends far beyond the iconic images of astronauts planting a flag on the lunar surface. It was a program that not only transformed our perspective on our place in the cosmos, but also acted as a powerful and often unappreciated catalyst for the development of the technologies that would underpin the digital revolution, including the nascent field of artificial intelligence. The primary driver for this was the immense and unprecedented challenge of navigating a spacecraft to another world. The Apollo guidance computer, the small but brilliant brain of the Apollo command module and the lunar module, was a true masterpiece of engineering. It was one of the first computers to use integrated circuits, a technology that was still in its infancy in the 1960s. The need to create a computer that was small enough, light enough, and reliable enough to fly to the moon was a major impetus for the miniaturization and the industrialization of the microchip. The technology that would later power everything from personal computers to smartphones. But the AGC's true innovation was in its software. The programmers at the MIT Instrumentation Laboratory, led by the brilliant Margaret Hamilton, had to invent many of the core concepts of modern software engineering to make the AGC work. They developed a sophisticated, real-time operating system that could handle multiple tasks simultaneously, prioritizing the most critical functions in the event of an overload. This asynchronous processing was a form of rudimentary AI, a system that could make its own intelligent decisions about how to allocate its limited computational resources. This capability famously saved the Apollo 11 lunar landing, when the AGC was being flooded with spurious data from a faulty radar switch. The computer recognized that it was being overloaded, and it autonomously rebooted and reprioritized its tasks, allowing Neil Armstrong and Buzz Aldrin to focus on the critical moments of their descent to the lunar surface. The lessons learned from the Apollo program. In terms of software reliability, of human-computer interaction, and of the need for intelligent, autonomous systems, had a profound and lasting impact on the design of all subsequent spacecraft. The onboard, AI-powered fault protection and sequencing systems of the Voyager probes, for example, were a direct intellectual descendant of the pioneering work that was done on the AGC. The Apollo program also highlighted the importance of the human factor in the design of complex technological systems. The interface between the astronauts and the AGC was a model of clarity and efficiency for its time. The display and keyboard unit, with its simple verb-noun command structure, was designed to be as intuitive and as error-proof as possible, allowing the astronauts to interact with the computer in a natural, conversational way, even in the high-stress environment of a lunar mission. This focus on human-computer interaction, on designing systems that are not just powerful, but also usable, is a key principle of modern AI design. The influence of Apollo can also be seen in the burgeoning commercial space industry of the 21st century. Companies like SpaceX and Blue Origin, with their focus on reusable rockets and on autonomous landing systems, are building on the legacy of innovation and of bold systems-level engineering that was established by the Apollo program. The sophisticated, AI-powered guidance, navigation, and control systems that allow a Falcon 9 rocket to autonomously land on a small drone ship in the middle of the ocean are a modern and spectacular manifestation of the same fundamental principles that were first developed to land a small, fragile lunar module on the surface of the moon a half-century ago. The Apollo program was more than just a series of missions. It was a catalyst, a forcing function, a national project of unprecedented scale and ambition that accelerated the development of a whole host of new technologies, and in doing so, it helped to lay the crucial and often invisible groundwork for the AI-powered digital world that we inhabit today. The synergy between machine learning and satellite technology has become one of the most powerful and transformative forces in our ability to monitor, to understand, and to manage our home planet. The vast and ever-growing constellation of Earth-observing satellites that orbit our planet are generating a torrent of data, a continuous, multispectral stream of information about our atmosphere, our oceans, our land, our ice. This data is a precious resource, but its sheer volume and complexity make it impossible for human beings to analyze manually. This is where machine learning comes in. Machine learning algorithms, particularly the deep learning techniques that have been developed in recent years, are incredibly adept at finding the subtle and often hidden patterns in these vast satellite-derived datasets. One of the most powerful applications of this synergy is in the field of environmental monitoring and climate change. Machine learning algorithms can be trained to automatically identify and to track a wide range of environmental changes from satellite imagery. They can map the extent of deforestation in the Amazon. They can monitor the retreat of glaciers in the Alps. They can track the spread of urban sprawl. They can detect the illegal fishing vessels in our oceans. They can do this with a speed, a scale, and an accuracy that was simply not possible just a few years ago. This provides scientists and policymakers with the crucial, timely, and objective data they need to understand the impacts of climate change and to develop effective mitigation and adaptation strategies. Another major area of impact is in disaster response. When a natural disaster, like a hurricane, a wildfire, or a flood, strikes, satellite imagery is a vital tool for assessing the damage and for coordinating the response efforts. Machine learning algorithms can be used to rapidly analyze the before and after images of a disaster zone, to automatically identify the damaged buildings, the flooded areas, the blocked roads. This information can be provided to the first responders on the ground in near real time, helping them to prioritize their efforts and to save lives. Agriculture is another field that is being transformed by this technology. By analyzing the multispectral data from satellites, a machine learning system can monitor the health of crops on a field-by-field basis. It can detect the early signs of disease or of water stress. It can estimate the crop yield, and it can provide farmers with the precise, actionable information they need to optimize their use of water, of fertilizer, of pesticides. This is the promise of precision agriculture, a more sustainable and more efficient way of feeding a growing global population. The synergy between machine learning and satellite technology is also driving a revolution in the design of the satellites themselves. The rise of smallsats and CubeSats, which are much smaller, cheaper, and faster to build than traditional large satellites, has led to a new paradigm of onboard processing. Instead of sending all the raw data back to Earth for analysis, which can be a bottleneck for a small satellite with a limited communication bandwidth, the machine learning algorithms can be run directly on the satellite's onboard computer. This allows the satellite to perform a first-pass analysis of the data in real time to identify the most interesting or important events, and to send back only the most valuable, processed information. This edge computing in space is making our satellite constellations not just more numerous, but also more intelligent, more autonomous, and more responsive. The Earth is a complex, dynamic, and interconnected system, and our ability to understand and to manage it sustainably is one of the greatest challenges of our time. The powerful and ever-evolving partnership between the global perspective of our satellites and the pattern recognition power of machine learning is one of the most important tools we have in rising to this challenge. The current landscape of space exploration is a vibrant and dynamic tapestry, a rich and complex interplay of governmental agencies, of a burgeoning commercial sector, and of an ever more capable global scientific community. We are living in a new, and in many ways, a second golden age of space. At the forefront of this new era is NASA's Artemis program, an ambitious and inspiring endeavor to return human beings to the moon. This time, to stay. Artemis is not just about planting a flag and taking a few rock samples. It is about building a sustainable, long-term human presence on the lunar surface and in lunar orbit. The program is a multifaceted international collaboration with a new, powerful rocket, the Space Launch System, a new deep space crew capsule, the Orion, and a new small space station in orbit around the moon, the Lunar Gateway. The goal of Artemis is to use the moon as a proving ground, a place to test the technologies, the operational concepts, and the human systems that will be needed for the next great leap in human exploration, a human mission to Mars. In parallel with these governmental efforts, the private, commercial space industry is undergoing a period of explosive growth and innovation. Companies like SpaceX, with its revolutionary, reusable Falcon 9 and Falcon Heavy rockets, have drastically reduced the cost of access to space, opening up a host of new possibilities for satellite deployment, for cargo delivery to the ISS, and for a new era of human spaceflight. The successful launch of the first crewed Dragon missions to the ISS has marked the return of human launch capability to the United States. And it has ushered in a new model of public-private partnership, where NASA acts as a customer for commercial launch services, rather than as the sole operator. Other companies, like Blue Origin and Virgin Galactic, are pioneering the field of suborbital space tourism, giving a new generation of private citizens the chance to experience the wonder of seeing the Earth from space. On the scientific front, the James Webb Space Telescope, which launched in December of 2021, is already exceeding our wildest expectations, providing breathtakingly beautiful and scientifically revolutionary images of the early universe, of the birth of stars and planets, and of the atmospheres of distant exoplanets. It is a new, powerful eye on the cosmos, a time machine that is allowing us to peer back to the very dawn of creation. And in the world of planetary science, NASA's Perseverance rover, which landed on Mars in February of 2021, is conducting a sophisticated, robotic search for the signs of past life in the ancient lake bed of Jezero Crater. It is collecting a cache of the most promising rock and soil samples, which will be returned to Earth by a future joint NASA-ESA mission for detailed analysis in our most advanced laboratories. This is a moment of immense excitement and of profound possibility in our exploration of the cosmos. The synergy between the long-term vision and the deep scientific expertise of our governmental space agencies and the agile, innovative, and often disruptive spirit of the commercial sector is creating a powerful and perhaps unstoppable momentum. We are, it seems, at the beginning of a new and truly transformative chapter in our long and enduring quest to understand and to explore the final frontier. Artificial intelligence is not just a future promise in space exploration. It is a present-day reality, a suite of powerful and increasingly sophisticated tools that are already being used to enhance almost every aspect of our robotic and human missions. We have already seen how AI is at the heart of the autonomous navigation systems of our Mars rovers. But its applications extend far beyond this. In the realm of scientific data analysis, machine learning is an indispensable tool. The search for exoplanets, for example, has been revolutionized by the use of AI. The Kepler and TESS space telescopes have generated a vast and overwhelming amount of data. The light curves of millions of stars, AI algorithms, particularly deep neural networks, can be trained to sift through this data and to identify the subtle, periodic dips in brightness that are the telltale signature of a transiting planet. A task that would be almost impossible for a human being to perform on this scale. AI is not just finding the planets, it is also helping us to characterize them. By analyzing the subtle variations in the light curve, an AI can help to determine the size, the mass, and the orbital period of a planet. And for the most promising candidates, AI can be used to analyze the spectroscopic data from telescopes like Hubble and Webb, to search for the chemical fingerprints of different molecules in the planet's atmosphere, and to help us assess its potential for habitability. AI is also playing a crucial role in mission planning and in resource management. The scheduling of the scientific observations for a complex observatory like the Hubble Space Telescope is a fiendishly difficult optimization problem. With thousands of competing requests and a host of complex, orbital, and instrumental constraints, AI-powered, automated scheduling systems are used to solve this problem, to create an observing schedule that is as efficient and as scientifically productive as possible. For a deep space mission, AI can be used to optimize the spacecraft's trajectory, to plan the complex sequence of engine burns and gravitational assists that are needed to reach a distant target with a minimum of fuel. And on board a spacecraft, AI can be used to manage the precious and limited resources of power and of data storage, ensuring that these resources are allocated in the most efficient way to meet the mission's scientific objectives. The communication between a deep space spacecraft and its mission control on Earth is another area where AI is having a major impact. The vast amounts of telemetry data that are downlinked from a spacecraft can be overwhelming. AI systems can be used to monitor this data in real time, to automatically detect any anomalies or off-nominal conditions, and to alert the flight controllers to any potential problems. This allows the human operators to focus their attention on the most critical issues, and it provides an extra layer of safety and of reliability for the mission. And as we look to the future, the role of AI is only set to grow. The next generation of robotic explorers will be even more autonomous, more intelligent, and more capable. The concept of a robotic geologist on Mars, a rover that can not just follow instructions, but can make its own scientifically driven decisions about where to go and what to study, is a major goal for future missions. And for the first, human missions to Mars. AI will be an indispensable partner, an intelligent assistant that can help the crew with everything from managing their life support systems to analyzing their scientific data to providing a form of psychological support and companionship on the long, lonely journey to another world. The integration of AI into our exploration of the cosmos is not about replacing human beings. It is about augmenting and extending our own natural capabilities. It is about creating a new and powerful form of human-AI symbiosis, a partnership that will allow us to explore further, to see more clearly, and to understand more deeply than ever before. The analysis of the vast and ever-growing data sets generated by our space missions is a challenge that has pushed the boundaries of our computational technologies and has given rise to a new and powerful paradigm of data-driven discovery. At the heart of this paradigm lies artificial intelligence, and in particular, the techniques of machine learning. A space mission, whether it be a telescope in orbit or a rover on another world, is essentially a data-gathering machine, and the data it collects is often complex, multidimensional, and incredibly voluminous. The images from the Hubble Space Telescope, the spectroscopic data from the Mars rovers, the telemetry from our deep space probes, all of this adds up to a torrent of information that is far too large and too complex for human beings to analyze in a comprehensive way. This is where machine learning excels. A machine learning algorithm is a system that can learn to recognize patterns in data without being explicitly programmed. You can train a neural network, for example, by showing it thousands of labeled images of galaxies, and it will learn on its own to distinguish between a spiral galaxy, an elliptical galaxy, and an irregular one. Once it is trained, it can then be let loose on a new, unlabeled data set, and it can classify millions of galaxies with a speed and an accuracy that can often match, or even exceed, that of a human expert. This is not just about automating a tedious task. It is about enabling a new kind of science. It allows us to perform large-scale, statistical studies of galaxy populations, to search for rare and unusual objects, and to test our theories of galaxy formation and evolution against a vast and unbiased data set. Another powerful application of machine learning is in the analysis of time series data, like the light curves from the Kepler and TESS missions. An AI can be trained to recognize the specific U-shaped dip in a star's brightness that is the signature of a transiting exoplanet, and it can distinguish this true planetary signal from the various other sources of stellar variability and instrumental noise that can mimic a transit. This has led to the discovery of thousands of new exoplanets, and it has allowed us to perform the first statistical census of the planets in our galaxy. Machine learning is also a crucial tool in the field of astrobiology. The search for life on other worlds is, in many ways, a search for anomalies, for chemical signatures in a planet's atmosphere that are out of equilibrium and cannot be easily explained by geology or by photochemistry. An AI can be trained on a vast library of simulated, non-biological planetary atmospheres, and it can then be used to search for real, observed atmospheres that deviate from these models, flagging the most promising candidates for follow-up observation. And in the world of planetary science, AI is being used to analyze the vast amounts of data from our Mars rovers, to create detailed 3D maps of the Martian terrain, to identify different types of rocks and minerals from their spectroscopic signatures, and to help the science team to piece together the geological history of the planet. The synergy between AI and space data is not just about analysis. It is also about simulation. The universe is a complex system, and many of its phenomena, like the merger of black holes or the formation of galaxies, are too complex to be described with simple, analytical equations. To understand these phenomena, we must rely on large-scale computer simulations. AI, and in particular, a technique called deep learning, is revolutionizing our ability to create and to analyze these simulations. An AI can learn the underlying physics of a simulation from the data it generates, and it can then be used to create a much faster surrogate model that can be used to explore a vast parameter space and to make new predictions. The integration of AI into the process of scientific discovery is a profound and transformative shift. It is a move away from a purely hypothesis-driven model of science to a more data-driven, exploratory one. And it is a shift that is allowing us to make sense of the beautiful, complex, and often overwhelming universe that our powerful new instruments are revealing to us. The autonomous rovers that we have sent to explore the surface of Mars are some of the most sophisticated and intelligent robots ever built. A beautiful and powerful testament to the synergy between artificial intelligence, robotics, and planetary science. The challenge of operating a robot on another planet, millions of miles from Earth, is a formidable one. The communication delay means that real-time joystick control is impossible. The rover must be given a high degree of autonomy, the ability to think and to act on its own. The first and most fundamental of these autonomous capabilities is navigation. The Martian terrain is a rocky, hazardous, and often unpredictable landscape. A rover must be able to perceive its environment, to identify potential hazards like steep slopes, large rocks, or soft sand, and to plot a safe path forward. The AutoNav system on the Curiosity and Perseverance rovers is a marvel of AI-powered robotics. As the rover drives, it takes a series of stereo images of the terrain in front of it. The onboard computer then uses these images to build a 3D terrain map of the immediate surroundings. It then analyzes this map, identifying the safe, the unsafe, and the no-go zones. And finally, it uses a path planning algorithm to compute a safe and efficient route to its next target, a route that it then executes, all without any input from the ground. This capability has dramatically increased the speed and the efficiency of our Martian exploration, allowing the rovers to cover far more ground and to visit far more interesting scientific targets than would be possible with a more human-intensive stop-and-go mode of operation. But the autonomy of these rovers extends beyond just driving. They are also, increasingly, autonomous scientists. The Aegis system, as we have mentioned, allows the rover to autonomously select its own scientifically interesting targets for a first-pass chemical analysis. This is a powerful tool for scientific triage. The rover can survey a wide area, identify the most unusual or promising rocks, and then send back the data on these high-value targets to the science team on Earth, allowing them to make a more informed decision about where to spend the rover's precious and limited time for a more detailed in situ analysis. The rovers are also capable of a high degree of autonomy in the operation of their complex. Robotic arms. The process of drilling a rock sample, of acquiring a soil sample, or of placing an instrument on a target is a complex and delicate sequence of motions, one that must be performed with a high degree of precision. While these sequences are typically commanded from the ground, the rover has a number of onboard, AI-powered safeguards that can detect if something is going wrong if the drill is binding, if the arm is about to collide with an obstacle, and can autonomously halt the operation and wait for further instructions. And as we look to the future, the autonomy of our robotic explorers is only set to increase. The next generation of Mars rovers may be equipped with even more advanced AI, allowing them to perform a much more sophisticated onboard scientific analysis. They could be robotic field geologists, capable of not just identifying interesting rocks, but of interpreting the geological context of an entire outcrop, of formulating their own scientific hypotheses, and of designing and executing their own follow-up observations to test those hypotheses. The future of planetary exploration may be one of a fleet of these intelligent, robotic scientists working collaboratively, sharing their data, and building a collective and ever-evolving understanding of another world, all with a minimum of human supervision. This is not to say that human explorers will not one day follow, but the robotic pioneers, our intelligent, autonomous, and ever-curious proxies, are the ones who are blazing the trail, who are mapping the new world, and who are doing the crucial, and often dangerous, work of preparing the way for our own eventual arrival. The synergy between artificial intelligence and our most powerful telescopes is opening up a new and breathtakingly beautiful window onto the universe. It is a partnership that is enhancing our vision, sharpening our focus, and allowing us to see the cosmos with a clarity and a depth that was unimaginable just a generation ago. One of the most powerful applications of this synergy is in the realm of adaptive optics. The primary limitation on the resolution of a large, ground-based telescope is not the size of its mirror, but the turbulence of the Earth's atmosphere. The same atmospheric twinkling that makes the stars appear to dance in the night sky also blurs and distorts the images of distant celestial objects, smearing the light from a sharp, point-like star into a fuzzy, boiling blob. Adaptive optics is a remarkable technology that can correct for this atmospheric distortion in real time. The system uses a wavefront sensor to measure the distortion in the incoming light from a star, and it then uses this information to control a small, deformable mirror in the telescope's light path. This mirror, which can have hundreds or even thousands of tiny, computer-controlled actuators on its back, can change its shape at a rate of up to 1,000 times per second, precisely canceling out the atmospheric blurring and producing an image that is almost as sharp as if the telescope were in space. AI is playing an increasingly important role in these adaptive optic systems. Machine learning algorithms can be used to analyze the data from the wavefront sensor and to predict how the atmospheric turbulence will evolve in the next few milliseconds, allowing the system to be more proactive and more precise in its corrections. This is leading to a new generation of extreme adaptive optic systems that are allowing our largest ground-based telescopes to take images that can rival, and in some cases even exceed, the sharpness of the Hubble Space Telescope. AI is also revolutionizing the way that we process the images and the data that are collected by our telescopes. The raw data from a modern astronomical camera is not a beautiful or full-color image. It is a series of noisy, monochromatic, and often distorted frames. The process of turning this raw data into a scientifically useful and aesthetically beautiful image is a complex one, involving a series of steps like cosmic ray removal, flat fielding, and image registration. AI, and in particular deep learning, is now being used to automate and to improve many of these image processing tasks. A neural network can be trained, for example, to recognize and to remove the telltale streaks of a cosmic ray hit, or to learn the subtle instrumental signatures that must be removed to create a clean, scientifically accurate image. But the role of AI is not just to clean up the images. It is also to help us to see what is hidden within them. The universe is full of faint, diffuse structures, the faint outer halos of galaxies, the tenuous streams of gas between them, the ghostly remnants of ancient stellar mergers. These structures are often hidden in the noise of a deep astronomical image. AI algorithms, with their uncanny ability to recognize subtle, large-scale patterns, can be used to enhance these faint features, to pull them out of the noise, and to reveal the hidden, underlying structure of the cosmos. And as we have seen, AI is also a powerful tool for the autonomous operation of our telescopes. The Vera C. Rubin Observatory, for example, will be a completely robotic facility. It's AI-powered, Scheduler software will decide, on its own, which parts of the sky to observe each night, optimizing its survey strategy to meet a wide range of scientific goals. And its alert pipeline will use machine learning algorithms to analyze the images as they are taken, to identify any transient events, a new supernova, a moving asteroid, a flaring star, and to send out an alert to the astronomical community in less than a minute. This is a new and exciting paradigm for observational astronomy. A move from a human-centered, a reactive mode of operation to a more autonomous, a more proactive, and a more data-driven one. The partnership between our great glass eyes on the cosmos and the new artificial minds that we are creating to help them to see is a partnership that is transforming our view of the universe. It is allowing us to see sharper, to see deeper, and to see in a new, more intelligent and more comprehensive way than ever before. The dream of artificial intelligence is a dream of creating a mind in a machine, a mind that can reason, that can learn, that can solve problems, that can perhaps, one day, even be creative and conscious. But this dream is also confronted by a series of deep and as yet unsolved limitations. These are not just technical challenges that will be overcome with more powerful computers or with bigger data sets. They are fundamental, conceptual hurdles that touch on the very nature of intelligence, of understanding, and of meaning. One of the most significant of these is the problem of brittleness. Many of our current state-of-the-art AI systems, particularly the deep learning models that have achieved such spectacular success in recent years, are incredibly powerful at the specific task they have been trained on. But they can be surprisingly brittle and can fail in unexpected and sometimes comical ways when they are presented with a situation that is even slightly outside of their training data. An image recognition system that can classify 1,000 different objects with superhuman accuracy can be completely fooled by a small, adversarial patch of pixels that is imperceptible to a human being. A self-driving car that can navigate a complex urban environment with ease can be thrown into confusion by an unusual weather condition or a strange, unforeseen road sign. This brittleness is a consequence of the fact that these systems do not, in a deep sense, understand the world. They are masters of statistical pattern recognition, but they lack the robust common-sense reasoning and the deep causal models of the world that are the hallmark of true human intelligence. For a high-stakes application like space exploration, this brittleness is a major concern. An autonomous rover on Mars cannot afford to be fooled by a strange shadow or an unusual rock formation. An AI that is managing the life support system of a spacecraft cannot afford to fail when it encounters a sensor reading that it has never seen before. The development of more robust, more reliable, and more explainable AI. An AI that can not just give an answer, but can also explain its reasoning, is one of the most important and active areas of research in the field today. Another major limitation is the problem of data hunger. Many of our most powerful machine learning models require a vast amount of labeled training data to achieve their high levels of performance. This is not always a problem for commercial applications, where companies can draw on the vast data sets of the internet. But for many scientific and engineering problems, particularly in a novel and data-scarce environment like space, this large, labeled data set simply does not exist. This has led to a great deal of research into new, more data-efficient learning techniques, such as transfer learning, where a model that has been trained on a large data set for one task can be adapted to a new, related task with a much smaller amount of data. And unsupervised learning, where an algorithm can learn to find the patterns and the structure in a data set without the need for any human-provided labels. And then there is the deepest and most profound limitation of all, the problem of consciousness, of subjective experience, of meaning. Our current AI systems are, for all their power, purely functional. They are incredibly sophisticated information processing machines, but there is no reason to believe that they have any inner life, any subjective experience, any genuine understanding of the concepts they are manipulating. They can process the word love. They can analyze its statistical correlations with other words. They can even write a beautiful poem about it. But they do not, in any meaningful sense, feel love. This is the hard problem of consciousness, and it is a problem that our current computational models of intelligence do not even begin to address. This is not just a philosophical curiosity. It has real, practical implications. An AI that is designed to be a companion for an isolated astronaut on a long-duration mission may be able to mimic the patterns of human conversation with incredible fidelity. But will it be able to provide the genuine empathy, the shared understanding, the authentic connection that is the true antidote to loneliness? This is an open and very important question. The limitations of AI are a sobering and necessary reminder that for all of our remarkable progress, we are still in the very early, infant stages of our quest to create a true artificial mind, and they are a reminder of the unique and perhaps irreplaceable value of our own human intelligence, with all its messiness, its irrationality, its creativity, and its deep and still mysterious capacity for genuine understanding and for conscious experience. The future of space exploration is a vast and largely unwritten book, a story of immense challenges and of even greater possibilities. The next few decades promise to be a time of profound transformation, a time when we may take our first tentative steps towards becoming a multiplanetary species. The return of humans to the moon, through the Artemis program, is the crucial first step on this journey. The moon is a world of immense scientific and strategic value. It is a natural laboratory for studying the history of the solar system, a potential source of resources like water and helium-3, and a perfect nearby proving ground for the technologies and the operational concepts that we will need to go to Mars. The establishment of a sustainable, long-term human presence on the moon, with a permanent base and an international community of astronauts and scientists, is a realistic and an inspiring goal for the coming decades. The human exploration of Mars is the next great leap. A human mission to Mars will be the most difficult and the most ambitious exploratory endeavor that our species has ever undertaken. It will be a journey of immense risk, of profound challenge, of unprecedented isolation. But it will also be a journey of unparalleled scientific discovery and of deep, transformative human experience. The search for past or present life on Mars is one of the most compelling scientific questions of our time. And the presence of human geologists and astrobiologists on the surface will be a game changer in this search. A human being, with their intuition, their creativity, and their ability to integrate multiple lines of evidence, can explore and can understand a complex geological environment in a way that a robot, however intelligent, simply cannot. The establishment of the first, small, self-sufficient human outpost on another world would be a milestone of almost unimaginable significance. A moment that would forever change our perspective on our place in the universe and on the future of our species. Beyond Mars, the future becomes more speculative, but no less inspiring. The development of new, advanced propulsion technologies, like nuclear thermal or nuclear electric propulsion, could drastically reduce the travel times to the outer solar system, opening up the beautiful and mysterious worlds of the gas giants and their moons to a new era of robotic, and perhaps one day, human exploration. The icy moons of Jupiter and Saturn, like Europa and Enceladus, which are thought to harbor vast liquid water oceans beneath their icy shells, are some of the most compelling targets in the search for extraterrestrial life in our own solar system. And the concept of asteroid mining, of learning to harness the vast, untapped resources of the solar system, is another long-term vision that could transform our future. But the future of space exploration is not just about going to new places. It is also about seeing the universe in new ways. The next generation of space telescopes, building on the legacy of Hubble and Webb, will continue to push the boundaries of our vision, searching for the faint, chemical signatures of life in the atmospheres of Earth-like exoplanets, and peering ever deeper into the dawn of time, and the new and revolutionary window of gravitational wave astronomy will allow us to hear the cosmos, to study the most violent and the most energetic events in the universe, like the merger of black holes and neutron stars, with a completely new sense. The future of space exploration is a future of profound and exciting possibilities. It is a future that will be shaped by a new and powerful synergy between human and robotic explorers, between governmental and commercial endeavors, between our relentless scientific quest for knowledge and our timeless human thirst for adventure. It is a future that is not guaranteed. It will require a sustained commitment, a global collaboration, a willingness to take risks, and a long-term vision. But it is a future that is within our grasp. It is a future that invites us to lift our eyes from our terrestrial concerns and to once again, as a species, to set our sights on the stars. The synergy between artificial intelligence and human decision-making is one of the most powerful and promising frontiers in the future of space exploration. The goal is not to create an AI that will replace the human astronaut, but to create an AI that will be a true collaborative partner, a system that can augment and extend our own natural cognitive capabilities, and can allow a small, isolated crew to function with the wisdom and the expertise of a vast terrestrial mission control. Imagine a medical emergency on a mission to Mars. An astronaut is suffering from a mysterious illness, with a complex and confusing set of symptoms. The crew medical officer is a highly trained physician, but they are not a specialist in every field of medicine. The communication delay with Earth makes real-time consultation impossible. This is where an AI-powered medical diagnostic system could be a lifesaver. The AI could have access to the entire accumulated knowledge of terrestrial medicine. It could analyze the astronaut's symptoms, their vital signs, their lab results, and it could compare this data to millions of case histories, to the latest medical research, to the known physiological effects of the space environment. It could then provide the crew medical officer with a ranked list of possible diagnoses, with the evidence for and against each one, and with a set of recommended treatment protocols. The AI would not be making the final decision. That would still be the responsibility of the human physician, but it would be providing them with a powerful, intelligent, and data-driven tool, a cognitive assistant that could dramatically enhance their ability to make the right decision in a high-stakes and highly uncertain situation. This same collaborative model can be applied to almost every aspect of a long-duration mission. In the realm of scientific research, an AI could be a partner in discovery. It could analyze the data that the crew is collecting in real time. It could identify the most interesting and anomalous results. And it could suggest new, follow-up observations, engaging the crew in a dynamic and interactive scientific dialogue. In the realm of spacecraft operations, an AI could be an intelligent systems expert. It could monitor the health of all the spacecraft systems. It could predict potential failures, and it could provide the crew with clear, step-by-step guidance on how to perform a complex repair. And in the realm of psychology, an AI could be a personal and personalized coach and companion. It could monitor the crew's stress levels, their sleep patterns, their social interactions, and it could provide them with tailored, evidence-based interventions to help them maintain their mental well-being, from a guided mindfulness meditation to a challenging cognitive game, to a simulated virtual reality walk on a beautiful terrestrial beach. The development of this kind of collaborative human-AI system is a major technological and ethical challenge. We must design these systems to be not just intelligent, but also transparent and trustworthy. The crew must be able to understand, at some level, how the AI is making its recommendations, and they must be able to trust that the AI is acting in their best interests. This will require a new kind of human-computer interaction, a new kind of partnership, one that is built on a foundation of mutual understanding, of clear communication, and of a shared sense of purpose. The future of human space exploration is not a future of humans versus machines. It is a future of humans with machines. It is a future where our own, natural, and still mysterious human intelligence is amplified, is supported, and is extended by the new and powerful artificial intelligences that we are creating to be our partners on the greatest adventure of all. The dream of autonomous space travel to distant planets, of a future where our robotic explorers are not just following a pre-programmed script, but are true, intelligent, and self-directed agents of discovery, is a dream that is being brought closer to reality by the rapid and accelerating advances in artificial intelligence. The key to this future lies in the development of AI systems that can not just learn from data, but can reason, can plan, and can make their own scientifically driven decisions in a complex and uncertain environment. The technique of deep learning, which has been the driving force behind the recent AI revolution, is a powerful tool for perception and for pattern recognition. A deep neural network can learn to recognize a particular type of rock from a rover's camera image with incredible accuracy. But true, scientific autonomy requires more than just perception. It requires cognition. It requires the ability to build a model of the world, to understand the causal relationships between things, and to use that model to reason about the consequences of different actions. This is the frontier of AI research today. The move from model-free systems that learn through trial and error to model-based systems that have a deeper, more conceptual understanding of their environment. For an autonomous spacecraft, this would mean having an on-board, AI-powered digital twin of itself, a detailed physics-based simulation of all its systems. This digital twin could be used to predict how the spacecraft will respond to different commands, to diagnose the root cause of a fault, and to test out different potential recovery strategies in a safe, virtual environment before they are executed in the real world. For an autonomous robotic scientist on the surface of Mars, this would mean having an onboard, AI-powered model of Martian geology. This model would be constantly updated with the new data that the rover is collecting, and it would be used to generate new scientific hypotheses about the history of the planet. The AI could then devise its own new experiments to test these hypotheses, deciding on its own which rock to drill, which sample to analyze, which new direction to explore. This is the vision of a truly closed-loop scientific process, a process where the robot is not just a data collector, but is an active and intelligent participant in the cycle of observation, of hypothesis, and of experimentation. The development of this kind of advanced cognitive AI is also essential for the safety and the efficiency of a long-duration mission. An autonomous spacecraft could optimize its own trajectory in real time, taking advantage of unexpected gravitational assists or avoiding unforeseen hazards. It could manage its own complex power and thermal systems, learning the optimal operating parameters for a given set of environmental conditions, and it could perform its own proactive health monitoring, constantly looking for the subtle, precursor signs of an impending equipment failure and taking preventative action before a small problem becomes a catastrophic one. And as we have seen, the advances in natural language processing are creating the possibility of a new, more natural and more intuitive form of communication between human beings and their intelligent robotic partners. An astronaut on the surface of Mars could have a natural conversational dialogue with their rover, asking it questions, giving it high-level commands, and engaging in a collaborative, scientific exploration of another world. The journey to creating a truly autonomous and truly intelligent space explorer is a long and challenging one. But it is a journey that is being accelerated every day by the remarkable and relentless progress in the field of artificial intelligence. It is a journey that promises to transform our ability to explore the cosmos and to usher in a new and even more exciting era of discovery. The use of artificial intelligence in the search for extraterrestrial life is a field of immense promise and of profound philosophical implications. It is a search that is, in many ways, perfectly suited to the unique capabilities of AI. The challenge of finding life beyond Earth is a challenge of sifting through a vast and largely empty cosmic haystack in search of a single and very subtle needle. As we have seen, one of the primary strategies in this search is the hunt for biosignatures in the atmospheres of distant exoplanets. A biosignature is a chemical fingerprint, a particular combination of gases that is a likely indicator of biological activity. The combination of oxygen and methane, for example, is a powerful biosignature, as these two gases would not be expected to coexist in large quantities in a planet's atmosphere without a constant biological source to replenish them. The James Webb Space Telescope is our first great instrument for searching for these biosignatures, but the data it produces is incredibly complex. To detect the faint absorption lines of these gases in the starlight that has passed through a planet's atmosphere requires a very high signal-to-noise ratio, and the interpretation of this data is a major challenge. There are many non-biological false positive scenarios that could mimic a biosignature. A geological process, for example, or a strange photochemical reaction in the planet's upper atmosphere, could produce a similar chemical signature. This is where AI can be a game changer. A machine learning algorithm can be trained on a vast and ever-growing library of simulated planetary atmospheres. This library would include a wide range of different planetary types, with different atmospheric compositions, different temperature profiles, and different host stars. And it would include both a large number of dead worlds, with atmospheres that are in chemical equilibrium, and a smaller number of simulated living worlds, with atmospheres that contain a variety of different hypothetical biosignatures. Once it is trained, this AI can then be used to analyze the real, observed data from a telescope like Webb. It can compare the observed spectrum to its vast internal library of possibilities, and it can calculate the probability that the observed signature is due to biology versus the probability that it is due to a non-biological false positive. This will be a powerful and essential tool for helping us to triage the vast number of exoplanets that will be discovered in the coming years, and for allowing us to focus our precious follow-up observation time on the most promising and most truly Earth-like of these worlds. Another related search is the search for extraterrestrial intelligence, the hunt for engineered technological signals from a distant civilization. For decades, SETI has been a process of scanning the radio sky, looking for a narrowband, artificial signal that would stand out against the natural, broadband noise of the cosmos. But the challenge is immense. The search space is vast, with billions of stars to listen to and billions of radio channels to monitor. AI is now being used to supercharge this search. A machine learning algorithm can be trained to recognize the specific characteristics of an artificial signal, and it can then be used to sift through the vast amounts of data that are collected by radio telescopes, like the Allen Telescope Array and the Green Bank Telescope, searching for a potential ET phone call with a speed and a sensitivity that was not previously possible. AI can also help us to broaden the search, to look for signals that are not the simple sine wave beacons that we have traditionally been searching for. A more advanced civilization might use a more complex and more efficient modulation scheme, one that might appear to us as just random noise. A sophisticated AI, with its ability to recognize complex, hidden patterns, might be able to detect this kind of advanced and perhaps even intentionally cryptic signal. The search for life beyond Earth is one of the most profound and most challenging of all scientific endeavors. It is a search that is pushing the limits of our technology, of our creativity, and of our very understanding of what it means to be alive. And in this great cosmic quest, artificial intelligence is not just a useful tool, it is becoming an essential and intelligent partner, a partner that is helping us to listen more carefully, to see more clearly, and to search more wisely for the faint and perhaps beautiful signatures of another form of life, somewhere in the vast and silent cosmic night. The management of the precious and finite resources on a long-duration human space mission is a challenge of immense complexity and of life-critical importance. It is a problem that is perfectly suited to the unique optimization capabilities of artificial intelligence. A human outpost on the Moon or on Mars will be a small and very fragile, closed-loop ecosystem. Every gram of water, every watt of power, every breath of air will be a precious resource that must be carefully managed and conserved. AI will be the intelligent and tireless steward of this fragile ecosystem. Consider the management of water. For example, the water on a Mars habitat will be in a constant cycle, from the drinking water supply to the crew, to the wastewater, to the water recovery system, to the plant growth chambers, and back again. And AI will be able to monitor this entire complex cycle in real time. It will be able to track the water levels in every tank, the flow rates in every pipe, the purity of the water at every stage of the recycling process, and it will be able to use this data to build a predictive model of the entire water system. This model will allow the AI to optimize the use of water, to schedule the water-intensive activities, like laundry or showers, at the times when there is a surplus, and to detect the subtle, early signs of a leak or a malfunction in the system, long before it becomes a critical problem. The management of power is another, equally critical, challenge. A Mars habitat will likely be powered by a combination of solar arrays and a small nuclear fission reactor. The output from the solar arrays will vary dramatically, depending on the time of day, the season, and the amount of dust in the Martian atmosphere. The AI will be able to manage this complex, hybrid power grid with a high degree of intelligence and efficiency. It will be able to predict the solar power output for the coming hours and days. Based on the weather forecast and the position of the sun, it will be able to manage the charging and the discharging of the habitat's batteries, ensuring that there is always enough stored power to get through the long Martian night. And it will be able to intelligently schedule the power-intensive activities, like the operation of the SRU plant or the scientific instruments, at the times when there is an abundance of solar power, a process known as load shifting. And in the event of a power anomaly, like the failure of a solar panel or a problem with the reactor, the AI will be able to autonomously reconfigure the power grid to shed the non-critical loads and to ensure that the life-critical systems are always kept running. The management of the habitat's food supply will be another complex optimization problem. The AI will be able to manage the operation of the space greenhouse, controlling the lighting, the temperature, the humidity, the nutrient delivery, to maximize the crop yield and to minimize the use of resources. It will be able to track the inventory of both the fresh-grown and the pre-packaged food. And it will be able to help the crew to plan their meals in a way that is both nutritionally optimal and that makes the most efficient use of the available resources. The role of AI in resource management on a long-duration mission is not about replacing the human crew. It is about empowering them. It is about providing them with a powerful, intelligent, and tireless assistant that can manage the immense complexity of their fragile, artificial ecosystem, freeing them up to focus on the more important and more uniquely human tasks of exploration, of science, of discovery, and of building a new, human future on another world. The dream of building a home for humanity on another world, of establishing the first, permanent, self-sustaining settlement on a planet like Mars, is a dream that is being brought closer to reality by a new and powerful convergence of technologies, artificial intelligence, advanced robotics, and autonomous construction. The challenge of building a large-scale habitat in a remote and hostile environment is a formidable one. To transport all the necessary materials, all the construction equipment, all the human labor from Earth to Mars would be a logistical and economic nightmare. The key to making a Mars settlement a reality is the ability to live off the land, to use the local in situ resources of the planet itself as the primary building material. And the key to unlocking this capability is the use of intelligent, autonomous, robotic construction systems. The vision is one of a precursor mission. A fleet of autonomous robots would be sent to Mars years before the first human crew ever arrives. This robotic vanguard would have a single, critical task to build the initial infrastructure of the first human settlement. They would be the surveyors, the miners, the construction workers of Mars. The process would begin with a team of autonomous rovers, equipped with ground-penetrating radar and other geological instruments, who would survey a wide area to identify the most promising locations for a settlement, locations with a high concentration of water ice, with a stable geological foundation, and with a favorable local climate. Once a site is chosen, a team of robotic miners would be deployed to excavate the Martian regolith and to extract the water ice. The water would be used not just for life support, but also as a source of hydrogen and oxygen for rocket propellant. The excavated regolith would become the primary building material for the habitat itself. This is where the technology of 3D printing, or additive manufacturing, becomes a game changer. A team of large, autonomous 3D printing robots would use the Martian soil, perhaps mixed with a binding agent brought from Earth or produced on site, to print the structural components of the habitat, the walls, the floors, the radiation shielding domes. This would be a slow, patient, and completely autonomous process, a robotic construction project that could take years to complete. And all of this would be managed and coordinated by a sophisticated on-site AI. This construction AI would be the foreman of the robotic work crew. It would plan the construction schedule. It would coordinate the movements of the different robots. It would monitor their progress, and it would troubleshoot any problems that arise. It would be a self-organizing, self-healing, and highly resilient construction system. A system that could build a city without any direct, real-time human supervision. By the time the first human crew arrives on Mars, they will not be landing on a barren, empty landscape. They will be arriving at a pre-prepared and fully functional outpost. Their habitat will be built. Their power systems will be running. Their water tanks will be full. Their greenhouse will be planted. They will be arriving not as desperate survivalist pioneers, but as the first proud citizens of a new human world. This vision of an AI-powered robotic construction on another planet is not just a science fiction fantasy. It is a serious and actively researched architectural and engineering concept. It is a vision that is being driven by the rapid and convergent advances in the fields of robotics, of AI, and of advanced manufacturing. And it is a vision that may hold the key to our future as a multiplanetary species. The relationship between human beings and the intelligent, artificial minds that we are creating is one of the most important and most complex issues of our time. And as we look to a future of long-duration space exploration, this relationship will be tested and defined in a new and unprecedented way. In the small, isolated, and high-stakes environment of a deep space mission, the collaboration between human astronauts and their AI partners will not be a matter of convenience. It will be a matter of survival. The design of these AI systems, therefore, must be guided not just by the principles of engineering and of computer science, but also by a deep and nuanced understanding of human psychology, of human factors, and of the ethics of human-AI interaction. The first principle of a successful collaborative AI is the principle of transparency or explainability. An AI that operates as a black box, that provides a recommendation or takes an action without being able to explain its reasoning, will not be trusted by a human crew, particularly in a life-critical situation. An astronaut needs to be able to ask the AI, "Why did you make that decision?" and to receive an answer that is clear, concise, and understandable. This is a major, and as yet unsolved, challenge in the field of AI. Many of our most powerful deep learning models are notoriously opaque, their decision-making processes hidden in the complex mathematical web of their neural networks. The development of explainable AI is a crucial area of research, one that is essential for building the foundation of trust that will be needed for a true human-AI partnership. Another key principle is the design of an intuitive and natural interface. The astronauts will need to be able to communicate with their AI partners in a way that is as seamless and as effortless as possible. This is where the advances in natural language processing are so important. The goal is to create an AI that an astronaut can talk to in a normal, conversational way, to ask questions, to give commands, to engage in a collaborative dialogue. The interface should also be multimodal, using a combination of voice, of graphics, of augmented reality, to present information in a way that is clear, that is context-aware, and that minimizes the cognitive load on the human user. The AI must also be designed to be adaptive, to be able to learn the individual preferences, the work styles, and the emotional states of each crew member, and to tailor its interactions accordingly. A good AI partner will know when to offer help, when to stay silent, when to provide a piece of data, and when to tell a joke. It will be, in a sense, an emotionally intelligent system. And finally, and perhaps most importantly, the design of a collaborative AI must be guided by a deep and well-thought-out ethical framework. The AI will be making decisions that can have a profound impact on the safety of the crew and the success of the mission. We must be very clear about the values that we are programming into these systems. The AI must be designed to be aligned with human values, to prioritize human safety above all else, and to be a benevolent and a trustworthy partner. This is not just a technical problem, it is a philosophical one. It requires a deep and ongoing conversation between the engineers who are building these systems and the humanists, the ethicists, and the society as a whole, who will be affected by them. The first human mission to Mars will be a journey of two kinds of intelligence, the natural and the artificial. The success of this journey will depend not just on the power of our rockets or the brilliance of our science, but on the wisdom and the foresight with which we design the relationship between these two very different forms of mind. The training of human astronauts to work effectively and collaboratively with their new artificial intelligence partners is a new and exciting frontier in the field of space human factors. It is a training that goes far beyond the traditional technical skills of operating a piece of equipment. It is about learning to build a relationship of trust, of communication, and of mutual understanding with a new and very different kind of mind. The first step in this training is to build a deep conceptual understanding of the AI's capabilities and its limitations. The astronauts must learn what the AI is good at and what it is not. They must understand the kinds of problems that are well suited to the AI's data-driven pattern recognition abilities and the kinds of problems that still require the more flexible, intuitive, and common-sense reasoning of a human being. This is not about memorizing a user manual, it is about developing a deep and almost intuitive feel for the AI's psychology. The second and most crucial step is to practice this collaboration in high-fidelity, team-based simulations. The astronauts, working alongside their AI partners, will be put through a wide range of realistic and often challenging mission scenarios. They will have to work with the AI to diagnose a complex systems failure, to plan a scientific exploration of a new and unknown terrain, to respond to a medical emergency. In these simulations, the astronauts will learn how to communicate effectively with the AI, how to interpret its recommendations, how to question its assumptions, and how to know when to trust its judgment and when to override it. These simulations will be a crucial two-way learning process. The astronauts will be learning how to work with the AI, and the AI, through its machine learning algorithms, will be learning how to work with the astronauts, adapting its behavior and its communication style to the specific needs and the preferences of its human crewmates. The training must also address the important and often subtle psychological aspects of the human-AI relationship. Astronauts must be prepared for the unique challenges of working with an entity that is incredibly intelligent, but not conscious. They must learn to avoid the trap of anthropomorphism, of projecting human emotions and intentions onto the AI. And they must also be prepared to deal with the potential for frustration, for misunderstanding, and even for a sense of competition that can arise in any complex, collaborative relationship. The training will also include a focus on the ethical dimensions of human-AI interaction. The crew will be presented with a series of ethical dilemmas, scenarios where the AI might make a recommendation that is technically optimal, but that conflicts with a fundamental human value. They will have to work through these scenarios, to discuss the ethical principles involved, and to develop a clear and shared understanding of how these kinds of conflicts will be resolved. The goal of this training is not to create a crew of passive AI operators. It is to create a crew of sophisticated and critical AI collaborators. It is to foster a new kind of hybrid intelligence, a deep and synergistic partnership between the human mind and the artificial one. The first crew to walk on Mars will be a crew of pioneers, not just in the exploration of a new world, but in the exploration of a new kind of relationship, a new kind of team, a new kind of future. A future where human beings and their intelligent, artificial creations work together to achieve things that neither could achieve alone. The profound and unrelenting psychological challenges of a long-duration mission to another world are a frontier that we are only just beginning to map. The stresses of isolation, of confinement, of being so far from home are immense, and in this extreme environment, artificial intelligence has the potential to be not just a useful tool, but a powerful, and perhaps even essential, therapeutic ally. One of the most promising applications of AI in this domain is in the creation of immersive and personalized virtual reality experiences. Imagine an astronaut, after a long and stressful day of work on the surface of Mars, being able to put on a VR headset and to be instantly transported to a beautiful and deeply familiar terrestrial environment. They could take a walk on their favorite beach. They could hike through a pristine mountain forest. They could even have a virtual visit with their family and friends in a simulated version of their own home. These VR experiences which could be powered by a sophisticated AI that can generate realistic and interactive environments, would be a powerful antidote to the sensory deprivation and the monotony of the Martian habitat. They would provide a much-needed psychological escape, a source of beauty, of novelty, and of a deep and healing connection to the natural world of Earth. AI can also be a powerful tool for the real-time and unobtrusive monitoring of an astronaut's mental health. By analyzing a combination of data from wearable, physiological sensors, from their speech patterns during their communications with the ground, and from their interactions with the habitat's computer systems, a machine learning algorithm could learn to recognize the subtle, early warning signs of stress, of anxiety, of depression. This is not about creating a Big Brother surveillance system. It is about creating a sensitive and intelligent digital guardian angel that can detect when a crew member might be struggling and can proactively offer support. This support could come in a variety of forms. The AI could suggest a personalized stress reduction intervention, like a guided mindfulness meditation or a biofeedback exercise. It could recommend a change in the astronaut's schedule, suggesting more time for rest or for recreation. Or it could facilitate a confidential and supportive conversation with a human psychologist on the ground. AI-powered chatbots or virtual assistants could also serve as a form of companionship and of emotional support. These systems, which are becoming increasingly sophisticated in their ability to understand and to generate natural, human-like conversation, could be a constant and reliable source of interaction for a lonely astronaut. They could be programmed to have different personalities, to have a sense of humor, to remember an astronaut's personal history and preferences. They could be a digital friend, a non-judgmental and always available sounding board, a partner for a game of chess, a source of encouragement and of positive reinforcement. And finally, AI can play a crucial role in maintaining the positive, social dynamics of the crew as a whole. An AI system could be used to analyze the patterns of communication within the crew, to identify the early signs of a potential conflict or of a breakdown in team cohesion. It could then provide a subtle and confidential intervention, perhaps by suggesting a team-building activity, or by facilitating a structured and mediated conversation to help the crew to work through their disagreements in a constructive way. The use of AI to support the psychological well-being of our explorers is a field that is still in its infancy. But it is a field of immense promise. It is a field that recognizes that the journey to other worlds is not just a physical and a technical challenge, it is also a profound and deeply human journey of the mind and of the heart. The increasing reliance on artificial intelligence in our exploration of the cosmos brings with it not just a host of new possibilities, but also a new set of deep and often challenging ethical considerations. As our AI systems become more autonomous, more intelligent, and more capable of making their own independent decisions, we are forced to confront a series of fundamental questions about responsibility, about accountability, about the very values that we are programming into these new artificial minds. One of the most significant of these is the issue of autonomous decision-making in life-critical situations. Imagine a future mission to Mars where an AI system is responsible for managing the habitat's life support system. A sudden and catastrophic failure occurs, and the AI must make a split-second decision that could have life or death consequences for the crew. It might have to choose, for example, between sealing off one section of the habitat to save the rest of the crew, or trying to save everyone, with a lower probability of success. Who is responsible for the outcome of that decision? Is it the programmers who wrote the AI's code? Is it the space agency that deployed the system? Is it the AI itself? This is the problem of accountability in autonomous systems, and it is a problem that we, as a society, are only just beginning to grapple with. The black box nature of many of our most advanced AI systems, particularly deep learning models, makes this problem even more acute. We can train a neural network to perform a task with incredible accuracy, but we often do not have a deep conceptual understanding of how it is making its decisions. This lack of transparency can be a major barrier to trust, particularly in a high-stakes environment like a human space mission. Another major ethical consideration is the potential for data bias. An AI system is only as good as the data it is trained on. If that data contains hidden biases, whether they be cultural, social, or historical, the AI will learn and will amplify those biases in its own decision-making. Imagine an AI system that is used to select the crew for a future space mission. If it is trained on the historical data of past astronaut corps, which have been predominantly white and male, it might learn to associate the characteristics of a good astronaut with those demographics, leading to a selection process that is systematically biased against women and minorities. The development of techniques for identifying and for mitigating bias in our AI systems, and the commitment to using diverse and representative training data is a crucial ethical imperative. And then there are the broader, more societal implications of our use of AI in space. As AI-powered robotic systems become more capable, there is a real and legitimate concern about their impact on the future of human employment in the space industry. Will the human geologist on Mars be replaced by a more efficient and less expensive robotic one? As we explore other worlds, we must also consider our ethical responsibilities to those worlds themselves. The principle of planetary protection is a cornerstone of our current robotic exploration program. But as we begin to contemplate the large-scale industrial activities that would be required for a self-sustaining human settlement on Mars, the mining of resources, the construction of habitats, the introduction of terrestrial life, we are forced to confront a new set of deep and often conflicting ethical questions. Do we have the right to fundamentally alter the environment of another world, even if it is to ensure our own long-term survival? These are not easy questions, and they do not have simple, technical answers. They are questions that require a deep and ongoing dialogue. A dialogue between the scientists and the engineers who are building these technologies, and the ethicists, the philosophers, the policymakers, and the public who will be affected by them. The future of AI in space is not just a matter of what we can do. It is a matter of what we should do. It is a future that requires not just technical brilliance, but also a deep and abiding ethical wisdom. The promise of artificial intelligence to enhance the safety of human spaceflight is one of its most compelling and most important applications. The space environment is, and will likely always be, an inherently risky one, but the intelligent and proactive use of AI has the potential to mitigate many of these risks, and to create a safer and more resilient future for our human explorers. One of the most powerful ways that AI can enhance safety is through the real-time and predictive monitoring of the spacecraft systems. A complex vehicle like a Mars transit habitat will have tens of thousands of sensors, all generating a constant stream of data about the health and the performance of its various components. An AI system can monitor this vast and often overwhelming stream of telemetry data, constantly looking for the subtle and often hidden patterns that might be a precursor to a failure. A traditional rule-based alarm system will only alert the crew when a parameter, like a temperature or a pressure, has already crossed a predefined red line. But a machine learning system can learn the normal operating behavior of a system in all its complex and multivariate glory, and it can detect a subtle deviation from this norm long before it becomes a critical failure. This is the power of predictive maintenance. It can allow the crew to intervene early, to perform a repair or to replace a component before a small problem cascades into a catastrophic one. AI can also play a crucial, life-saving role in the event of an emergency, in a high-stress, time-critical situation, like a fire or a depressurization. The human crew can become overwhelmed, their cognitive abilities degraded by the effects of stress. An AI system, which is immune to these human frailties, can be an invaluable partner in a crisis. It can rapidly diagnose the problem. It can access the relevant emergency procedures from its vast onboard database. And it can provide the crew with clear, concise, and prioritized guidance on the steps they need to take to save themselves and their vehicle. This is not about the AI taking over. It is about the AI acting as a calm, intelligent, and deeply knowledgeable assistant. A cognitive co-pilot that can help the human crew to perform at their best when they need it the most. The safety of the crew is also intimately tied to their own physical and psychological health. As we have seen, an AI can be a powerful tool for monitoring the crew's well-being, for detecting the early signs of a medical or a psychological issue, and for providing them with personalized preventative care. And in the design phase of a mission, AI can be used to create a safer and more resilient spacecraft. Generative design algorithms can be used to optimize the structural integrity of a vehicle, to design a more effective radiation shield, or to create a habitat layout that is more ergonomically and psychologically sound. The use of AI to enhance the safety of human spaceflight is a field of immense promise. It is a field that is still in its early stages, and there are many significant technical and ethical challenges that must be overcome. But it is a field that holds the key to our future as a spacefaring species. The journey to the stars will always be a dangerous one, but by creating a new and powerful partnership between human and artificial intelligence, we can make that journey a little bit safer, a little bit more resilient, and a little bit more likely to succeed. The exploration of the cosmos is, by its very nature, an interdisciplinary endeavor. It is a quest that requires the knowledge, the skills, and the perspectives of a vast and diverse range of scientific and technical fields. The astronomer who studies the light from a distant galaxy, the planetary scientist who analyzes the geology of Mars, the astrobiologist who searches for the signs of life, the engineer who designs the rocket, the computer scientist who writes the software, the medical doctor who cares for the crew. All of these, and many more, are essential partners in this great human adventure. The complexity of a modern space mission is so immense that no single individual and no single discipline can possibly grasp it in its entirety. The design of a new space telescope, for example, requires the collaboration of optical engineers, of mechanical engineers, of thermal engineers, of software engineers, of astrophysicists. The planning of a human mission to Mars requires the expertise of orbital mechanics, of propulsion engineers, of life support specialists, of medical doctors, of psychologists, of human factors experts. The search for life on another world is a profoundly interdisciplinary quest, one that brings together the insights of astronomy, of geology, of chemistry, of biology. This deep and often challenging. Collaboration between different disciplines is one of the hallmarks of space exploration. It is a process that forces us to break down the traditional academic silos, to learn each other's languages, to appreciate each other's perspectives, and to work together to solve problems that are far too complex for any single field to tackle on its own. And the integration of artificial intelligence into this landscape is adding a new and powerful dimension to this interdisciplinary synergy. AI is not just another tool in the toolbox. It is becoming a common language, a shared platform, a unifying framework that can connect and can enhance the work of all these different disciplines. A machine learning algorithm, for example, can be used to analyze the data from a wide range of different instruments, from an astronomer's telescope to a geologist's spectrometer to a biologist's microscope. It can find the hidden, cross-disciplinary patterns and correlations in this data. Patterns that a human specialist, working within their own, narrow domain, might never see. This is leading to a new, more holistic, and more data-driven approach to planetary science, a field known as planetary systems science, where a planet is studied not as a collection of separate geological, atmospheric, and biological systems, but as a single, complex, and interconnected whole. The development of AI for space exploration is also, in itself, a profoundly interdisciplinary endeavor. It requires the close collaboration of computer scientists, who design the algorithms, of software engineers, who write the code, of robotics engineers, who build the hardware, and of the domain experts, the astronomers, the planetary scientists, the astronauts who provide the knowledge and the context that the AI needs to function intelligently. This is a field where the lines between the disciplines are constantly being blurred, where the computer scientist must learn about geology, and the geologist must learn about machine learning. The future of space exploration is a future of deep and ever more powerful interdisciplinary collaboration. It is a future where our ability to solve the great scientific and technical challenges of our time will depend not just on the depth of our specialized knowledge, but on our ability to connect, to communicate, and to create across the boundaries of our different fields. And in this great collaborative symphony of human knowledge, artificial intelligence is poised to become one of the most important and most harmonious of all the instruments. The development of artificial intelligence for the unique and demanding environment of space exploration is a task that requires a new kind of team, a new kind of collaborative process, one that brings together the deep domain expertise of the space community with the cutting-edge, algorithmic expertise of the AI community. This is a marriage of two very different cultures, of two very different ways of thinking, and it is a marriage that is essential for the success of our future. AI-powered missions. The team that is building an AI for an autonomous Mars rover, for example, is a beautiful and complex interdisciplinary ecosystem. There are the computer scientists and the machine learning engineers, who are the experts in designing and in training the neural networks and the other AI algorithms. There are the robotics engineers, who are the experts in the hardware of the rover, in its sensors, its actuators, its mobility systems. There are the software engineers, who are the experts in writing the robust, reliable, and real-time code that is the backbone of the rover's operating system. And then there are the planetary scientists, the geologists, the astrobiologists, who are the domain experts, the people who understand the scientific questions that the rover is trying to answer, and who can provide the crucial scientific context that the AI needs to make its intelligent decisions. The process of developing the AI is a deeply iterative and collaborative one. The planetary scientists will work with the AI team to define the scientific goals for the system. They might say, we want the AI to be able to identify rocks that are likely to have been formed in the presence of water. The AI team will then take this high-level goal and translate it into a specific technical problem. They will work with the scientists to create a large, labeled training data set, a collection of thousands of images of different types of rocks, each one labeled by a human geologist as either interesting or uninteresting. They will then use this data set to train a deep neural network, an algorithm that can learn to recognize the subtle, visual features that distinguish a scientifically promising rock from a boring one. The trained model is then tested, both in simulation and on a physical prototype rover in a Mars yard, a terrestrial test bed that mimics the Martian terrain. The planetary scientists are an integral part of this testing process. They act as the adversaries, trying to fool the AI, presenting it with ambiguous or unusual rocks, and helping the AI team to understand where the system is succeeding and where it is failing. This feedback is then used to refine the algorithm to collect more training data to improve the model. It is a continuous and often challenging feedback loop, a dialogue between the human expert and the artificial one, and the collaboration extends beyond just the development phase. Once the rover is on Mars, the interdisciplinary team continues to work together. The AI will be autonomously selecting its own scientific targets, but the human science team on the ground is always in the loop. They will review the AI selections. They will provide their own expert interpretation of the data, and they will make the final decision about where to send the rover for a more detailed in situ analysis. It is a model of human-on-the-loop collaboration, a partnership that combines the speed, the scale, and the tirelessness of the AI with the deep contextual understanding, the creativity, and the ultimate scientific judgment of the human expert. This kind of deep interdisciplinary collaboration is the key to unlocking the full potential of AI in space exploration. It is a process that is as much about building human relationships as it is about building intelligent machines, and it is a process that is creating not just a new generation of smarter and more capable space explorers, but also a new and more collaborative and more powerful way of doing science itself. The vast and ever-growing torrent of data that is flowing back to us from our space missions is a precious and beautiful resource, a new digital window onto the cosmos. But it is also a profound challenge. The sheer volume and complexity of this data is far beyond the capacity of the human mind to analyze in a comprehensive way. This is where the role of the data scientist and the powerful tools of artificial intelligence and machine learning becomes absolutely essential. A data scientist in the field of space exploration is a new kind of explorer, a person who journeys not into the physical vastness of space, but into the vast and often bewildering digital universe of our scientific data. Their role is to be the bridge between the raw and often messy data that is collected by our instruments and the deep scientific insights that are hidden within it. The process begins with the data itself. A data scientist must first understand the data, its format, its quality, its biases, its limitations. They must work closely with the instrument scientists and the engineers to understand how the data was collected and what the sources of noise and of systematic error might be. They must then clean and pre-process the data to prepare it for analysis. This is often the most time-consuming and the least glamorous part of the job, but it is also the most crucial. The next step is the analysis itself. A data scientist has a wide range of tools at their disposal, from traditional statistical techniques to the more advanced and often more powerful techniques of machine learning. They might use a clustering algorithm to find the natural groupings of stars in a large stellar survey. They might use a regression model to find the relationship between a galaxy's mass and its rate of star formation. Or they might, as we have seen, train a deep neural network to classify galaxies, to find exoplanets, or to identify the subtle chemical signatures of a potential biosignature. The choice of which tool to use is a matter of both art and science. It requires a deep understanding of the scientific question being asked, and a deep and often intuitive feel for the structure of the data itself. But the role of the data scientist is not just to run the algorithms, it is also to interpret the results. An AI can find a correlation in a data set, but it cannot, on its own, tell you whether that correlation is a meaningful causal relationship or just a spurious statistical fluke. It is the job of the data scientist, working in close collaboration with the domain experts, the astronomers and the planetary scientists, to make this crucial scientific judgment. And finally, the data scientist is a storyteller. They must be able to take the complex and often abstract results of their analysis and to communicate them in a way that is clear, that is compelling, and that is understandable, both to their scientific colleagues and to the wider public. This is where the art of data visualization becomes so important. A well-designed graph, a beautiful image, an interactive, data-driven website, these can often be far more powerful and more effective at conveying a scientific insight than a dense technical paper. The role of the data scientist in space exploration is a new and rapidly evolving one. It is a role that requires a unique and powerful combination of skills, the mathematical rigor of a statistician, the computational prowess of a computer scientist, the creative curiosity of a scientist, and the communication skills of a storyteller. They are the new and essential navigators of our digital cosmos, the people who are turning the vast and often chaotic ocean of our data into the beautiful and meaningful maps that are guiding our journey of discovery. The deep and intimate connection between the study of the brain and the development of artificial intelligence is a story of a long and often fruitful two-way dialogue. From the very beginning of the field of AI, the human brain has been a powerful source of inspiration. The first neural networks, developed in the 1950s, were a direct, albeit highly simplified, attempt to model the interconnected, computational structure of biological neurons. And while the field of AI has often diverged from a strict biological mimicry, the brain remains a constant and humbling benchmark for the kind of flexible, robust, and general intelligence that we are ultimately trying to create. As our understanding of the brain through the remarkable advances in the field of neuroscience has deepened, it has provided a new and richer source of inspiration for AI research. Our growing knowledge of the brain's different learning systems, for example, is influencing the design of new, more powerful machine learning algorithms. The brain does not have a single, monolithic learning mechanism. It has multiple, interacting systems. There is the hippocampal system, which is responsible for the rapid, one-shot learning of new episodic memories. And there is the neocortical system, which is responsible for the slow, incremental learning of statistical regularities and of general knowledge. The interplay between these two systems is thought to be what allows us to both learn quickly from new experiences and to build a stable and general model of the world. AI researchers are now trying to build systems that mimic this complementary learning systems architecture, in the hope of creating AIs that are both more data efficient and less prone to the problem of catastrophic forgetting, where a neural network that is trained on a new task can suddenly forget everything it had learned before. The brain's use of attention is another area of inspiration. When we perceive a complex scene, we do not process all the information with equal weight. Our brain has a sophisticated attentional mechanism that allows it to focus its computational resources on the most relevant parts of the input, while ignoring the rest. This is an incredibly efficient strategy, and it is one that has been successfully incorporated into many of our most advanced deep learning models, particularly in the fields of image recognition and of natural language processing. But the dialogue between neuroscience and AI is not a one-way street. AI is also becoming an increasingly powerful tool for helping us to understand the brain itself. The brain is an incredibly complex system, with billions of neurons and trillions of connections. Trying to understand how this system gives rise to thought, to perception, to consciousness is perhaps the greatest scientific challenge of all. The traditional reductionist approach of studying single neurons or small circuits is essential, but it is not enough. We also need a more holistic systems-level understanding, and this is where AI, and in particular large-scale neural network modeling, can be an invaluable tool. By building large and increasingly realistic computational models of different brain regions, and by comparing the behavior of these models to the real observed data from neuroimaging and neurophysiological experiments, we can begin to test our theories about how the brain works in a new and more rigorous way. This synergy between neuroscience and AI is particularly relevant to the challenges of space exploration. The brain is a remarkable and remarkably resilient information processing system, It is capable of adapting to novel environments, of learning new skills, of making robust decisions in the face of uncertainty. Understanding the principles that underlie this resilience and adaptability is crucial for designing the training programs and the support systems that will be needed to keep our astronauts' minds healthy and sharp on a long-duration mission. And the AI systems that we are designing to be their partners on this journey will be all the more powerful, all the more robust, and all the more trustworthy if they are inspired by the deep and beautiful wisdom of the 3 billion-year-old biological computer that we all carry around inside our own heads. The rise of the commercial space industry, the new space movement, is one of the most exciting and transformative developments in the history of our exploration of the cosmos. For decades, space was the exclusive domain of a small number of large governmental agencies. But in the last 2 decades, a new and vibrant ecosystem of private entrepreneurial companies has emerged. Companies that are bringing a new, and often disruptive, spirit of innovation, of agility, and of commercial ambition to the final frontier. This new public-private partnership is a powerful engine for accelerating the pace of innovation, particularly in the field of artificial intelligence. Private companies, which are often more agile and less bureaucratic than their governmental counterparts, are able to iterate and to experiment with new technologies at a much faster rate. A company like SpaceX, for example, has been able to develop and to perfect the incredibly complex AI-powered technology of reusable rocket landings in a remarkably short period of time, a feat that is a testament to their culture of rapid, iterative, and data-driven engineering. This agility is also a major advantage in the fast-moving field of AI. The state-of-the-art in machine learning is advancing at an exponential pace, and private companies, which are often more closely connected to the vibrant academic and industrial AI research community, are able to rapidly incorporate these new cutting-edge techniques into their systems. Private companies also have access to a different and often larger pool of capital. While governmental space agencies are dependent on the often fickle cycle of public funding, private companies can tap into the vast resources of the venture capital market and of wealthy visionary investors. This allows them to make large, long-term investments in high-risk, high-reward technologies, including the development of advanced AI-powered systems. The collaboration between the public and the private sectors creates a powerful synergistic effect. NASA and other space agencies can leverage the innovation and the cost-effectiveness of the private sector, acting as a customer for services like cargo and crew transportation to the ISS, and freeing up their own limited resources to focus on the more challenging and more scientifically driven tasks of deep space exploration. The private companies, in turn, benefit from the deep and often decades-long technical expertise and the scientific knowledge base of the governmental agencies. This sharing of resources, of expertise, and of risk is creating a new and more powerful model for space exploration. We are seeing this synergy at play in the development of AI for Earth observation. A number of private companies, like Planet and Maxar, have deployed vast constellations of small Earth imaging satellites. They are using sophisticated AI-powered analytics platforms to process the data from these satellites and to provide a wide range of commercial services, from monitoring agricultural yields to tracking global supply chains. And they are also partnering with governmental agencies and with scientific researchers, providing them with access to this unprecedented and continuously updated data set of our home planet. This public-private partnership is creating a virtuous cycle, a feedback loop, where the demands of the commercial market are driving the innovation in AI and in satellite technology, and where the new capabilities of these technologies are, in turn, enabling a new era of scientific discovery and of a more sustainable management of our planet's resources. The future of space exploration is a future of collaboration, A future where the bold, dual, long-term vision of our public space agencies is amplified and is accelerated by the dynamic and often disruptive power of private enterprise. The integration of artificial intelligence into the complex and high-stakes world of space exploration is a journey that is not just about technological innovation. It is also a story of a deep and co-evolving relationship between the fields of robotics and of software engineering. The robots that we send to explore other worlds are more than just mechanical bodies. They are embodied AI, physical systems that must be able to perceive, to reason, and to act in a complex and often unstructured environment. The challenges of building a robot that can function autonomously on the surface of Mars are a powerful driver for innovation in the field of robotics. The need to navigate a rocky and unpredictable terrain has spurred the development of new, more robust, and more agile mobility systems. The need to manipulate rocks and to collect samples has led to the development of more dexterous and more sensitive robotic arms and hands. And the need to perceive the environment in a rich and detailed way has led to the development of a sophisticated suite of sensors, from stereo cameras and laser scanners to ground-penetrating radar and chemical spectrometers. But all of this sophisticated hardware would be useless without the equally sophisticated software that controls it. The development of AI for space robotics is a major challenge for the field of software engineering. The software for a Mars rover is one of the most complex and most reliable pieces of code ever written. It is a real-time, multi-threaded, and highly fault-tolerant operating system. A system that must be able to manage the rover's resources, to schedule its activities, and to respond to unexpected events, all with a high degree of autonomy. The AI algorithms for navigation, for science target selection, for fault diagnosis, all of these must be carefully designed, rigorously tested, and seamlessly integrated into this complex software architecture. The extreme environment of space, with its high radiation levels, its extreme temperatures, and its lack of any possibility for a reboot by a human technician, places an incredible premium on software reliability. The software engineers who write the code for our deep space missions are some of the most disciplined and most meticulous programmers in the world. They must think about every possible failure mode. They must write code that is robust to unexpected inputs. And they must test their software with a level of rigor that is almost unheard of in the commercial software world. The synergy between AI, robotics, and software engineering in space exploration is a powerful two-way street. The demands of building an intelligent, autonomous robot for another world are pushing the boundaries of all three fields. And the advances in these fields are, in turn, enabling a new generation of more capable and more ambitious space missions. The lessons that we are learning about how to build robust, reliable, and intelligent autonomous systems in the most challenging environment imaginable are lessons that have a profound and direct application to the development of robotics and of AI here on Earth. The AI-powered, self-driving rovers on Mars are the direct ancestors of the self-driving cars that are beginning to appear on our own roads. The sophisticated, robotic arms on the space station are a proving ground for the next generation of industrial and surgical robots. And the high-reliability, fault-tolerant software that we write for our spacecraft is a model for the kind of software that will be needed for the life-critical autonomous systems of our future, from our power grids to our air traffic control systems. Space exploration is more than just a quest to understand the universe. It is a powerful engine of technological innovation, an engine that is driving the development of the intelligent, robotic, and software-defined world of our own. Terrestrial future. The journey into space is a journey into an environment of profound and unrelenting risk. From the violent, controlled explosion of a rocket launch to the cold, unforgiving vacuum of space, to the fiery, high-G ordeal of re-entry. Every phase of a human space mission is fraught with potential danger. The management of this risk is the single most important and most challenging aspect of human spaceflight. The risks are numerous and varied. There are the technical risks, the possibility of a failure in one of the thousands of complex and often single-point critical components of the spacecraft: a faulty O-ring, a piece of foam insulation, a stuck valve. These are the kinds of small technical failures that have led to some of the greatest tragedies in the history of space exploration. There are the environmental risks, the constant threat of micrometeoroid and orbital debris impacts, the invisible danger of space radiation, the extreme temperatures, the vacuum of space itself. And then there are the human risks, the possibility of a medical emergency, of a psychological breakdown, of a simple human error in a life-critical situation. The management of these risks is a deep and multi-layered process. It begins with design, with the engineering principle of redundancy. All of the critical systems on a spacecraft are designed with multiple independent backups. There are multiple computers, multiple communication systems, multiple life support systems. The goal is to design a system where no single failure can lead to a catastrophic loss of the crew or the vehicle. The process also involves a relentless and obsessive approach to testing. Every component, every subsystem, every line of software code is subjected to a battery of rigorous tests on the ground, designed to simulate the harsh environment of space and to find any potential weaknesses before the mission ever flies. And the process is guided by a deep and often hard-won culture of safety. The history of human spaceflight has been punctuated by tragedy, by the loss of the Apollo 1 crew in a fire on the launch pad, by the loss of the Challenger and the Columbia space shuttles. These tragedies have been painful, but they have also been powerful and necessary learning experiences. They have led to a profound and deeply ingrained culture of safety within our space agencies, a culture that is based on the principles of open communication, of a healthy respect for the inherent dangers of the endeavor, and of a willingness to listen to dissenting opinions. But for all of our planning, for all of our testing, for all of our procedures, there will always be an element of the unknown, of the unexpected. The environment of space is simply too complex, and our technologies are simply too new to be able to anticipate and to mitigate every possible risk. This is where the skill, the training, and the resilience of the human astronaut becomes the ultimate final layer of safety. The crew is trained to be not just pilots and scientists, but to be resourceful and creative, problem solvers. The story of Apollo 13, the successful failure, is a powerful testament to this. When an oxygen tank exploded on the way to the moon, crippling their spacecraft, the crew and the mission control team, working together, were able to improvise a series of ingenious solutions that allowed them to use their lunar module as a lifeboat and to return safely to Earth. This is the human factor at its very best. It is the ability to think on one's feet, to adapt to a novel situation, to work together as a team, and to find a way to survive against all odds. The journey into space will always be a risky one. There is no such thing as a safe rocket, but it is a risk that we, as a species, have always been willing to take. It is a risk that is driven by our innate and enduring desire to explore, to discover, and to push the boundaries of what is possible. And it is a risk that we can and must manage with a combination of brilliant engineering, of rigorous discipline, and of a deep and humble respect for the powerful and often unforgiving nature of the cosmos. The deployment of artificial intelligence in the high-stakes and life-critical environment of space exploration is a task that is fraught with its own unique set of challenges and risks. While AI has the potential to be a powerful tool for enhancing the safety and the capability of our missions, it also introduces a new set of failure modes, of vulnerabilities, and of ethical dilemmas that must be carefully considered and managed. One of the primary challenges, as we have discussed, is the brittleness of many of our current AI systems. A deep learning model that has been trained to perform a specific task with superhuman accuracy can be surprisingly fragile when it is presented with a novel or an unexpected input. This is a major concern for an autonomous system that must be able to function reliably in the dynamic and often unpredictable environment of space. An autonomous rover on Mars that is fooled by an unusual lighting condition or a life support AI that misinterprets a faulty sensor reading could lead to a catastrophic failure. The development of AI systems that are not just intelligent, but also robust and resilient, and that have the ability to recognize when they are outside of their domain of expertise and to gracefully fail safe, is a critical area of research. Another major challenge is the black box nature of many of our most powerful AI models. The decision-making process of a deep neural network, with its millions of interconnected parameters, can be incredibly difficult for a human being to understand and to interpret. This lack of transparency can be a major barrier to trust. How can an astronaut be expected to trust the recommendation of an AI in a life-critical situation if they have no understanding of how that recommendation was arrived at? The development of explainable AI, of systems that can not just provide an answer, but can also provide a clear and understandable rationale for that answer, is essential for building the foundation of trust that will be needed for a true human-AI partnership. The integration of AI into our existing legacy space systems is another significant hurdle. Many of our current spacecraft and our operational protocols were not designed with AI in mind. The process of safely and reliably integrating a new AI-powered system into this complex, and often aging, technical and human ecosystem is a major systems engineering challenge. It requires a deep and careful consideration of the human-computer interface, of the training of the human operators, and of the new, and often subtle, failure modes that can be introduced by the interaction between the human and the AI. And then there are the ethical considerations. As our AI systems become more autonomous, they will increasingly be faced with situations where they must make decisions that have a real, and sometimes profound, ethical dimension. An autonomous scientific rover on Mars, for example, might be faced with a choice between two equally promising scientific targets. How should it make that choice? Should it be programmed to maximize the a priori scientific value of the data it collects, or should it have some element of randomness, of curiosity, of a willingness to explore the unknown? An AI that is managing the resources on a long-duration mission might have to make a decision about how to allocate a limited resource, like water or medical supplies, between different crew members. What ethical principles should guide that decision? These are not easy questions, and they do not have simple, technical answers. They require a deep and ongoing dialogue between the AI developers, the mission planners, the crew, and the wider society. The deployment of AI in space is not just a technical challenge. It is a human one. It is a challenge that requires us to be as thoughtful, as rigorous, and as wise in the design of our intelligent new partners as we are in the design of our powerful new machines. The challenge of ensuring the reliability of our AI systems in the life-critical and unforgiving environment of space is one of the most important and most difficult tasks in the field of software engineering. The traditional methods of software verification and validation, which have been developed over decades for our terrestrial and often less critical systems, are not always sufficient for the new, and often more opaque world of machine learning and of autonomous systems. A new and more comprehensive approach to AI safety and reliability is needed. This approach begins with the data. A machine learning model is only as good as the data it is trained on. To build a reliable AI, we must start with a high-quality, diverse, and representative training dataset. This dataset must be carefully curated to ensure that it is free of errors and of biases. And it must be large enough to cover the full range of conditions and of scenarios that the AI is likely to encounter in its operational environment. But even the best training data is not enough. We must also develop new, more rigorous techniques for the testing and the validation of our AI models. This goes beyond simply measuring the model's accuracy on a held-out test set. It involves a process of adversarial testing, where we actively try to find the inputs that will cause the AI to fail. It involves the use of formal verification techniques, where we can mathematically prove that the AI's behavior will always stay within a certain safe envelope. And it involves the extensive use of high-fidelity and physics-based simulation, where we can test the AI's performance in a vast number of different and often off-nominal scenarios. Another key principle of reliable AI design is redundancy. A life-critical, AI-powered system should not be a monolith. It should be a diverse and a redundant system, composed of multiple, independent AI models, perhaps trained on different data sets or using different algorithmic approaches. These different models can then vote on the best course of action, and any significant disagreement between them can be flagged as a sign of uncertainty, a signal to the human operator that they need to take a closer look. The human in the loop is the ultimate layer of safety and of reliability. An AI system in a critical application should not be a fully autonomous black box. It should be a collaborative partner, a system that is designed to work with a human operator, not to replace them. The AI should be designed to be transparent, to be able to explain its reasoning to the human. And the human operator must be trained to be a sophisticated and critical user of the AI, to understand its strengths and its weaknesses, and to know when to trust its judgment and when to override it. And finally, we must have a process of continuous learning and adaptation. The world is not static, and an AI that is deployed in a complex and evolving environment, like a long-duration space mission, must be able to learn and to adapt over time. This requires the ability to safely and reliably update the AI's model with the new data that is being collected during the mission. This is a major technical challenge, as a poorly executed update could introduce new and unforeseen errors into the system. The development of safe and reliable, lifelong learning systems is a key area of AI research. The challenge of building a reliable AI for space is a formidable one, but it is a challenge that we are learning to meet through a combination of rigorous engineering, of innovative research, and of a deep and humble appreciation for the immense complexity and the high stakes of the endeavor. The increasing reliance on autonomous AI-powered systems in our exploration of the cosmos brings with it not just a host of new possibilities, but also a new set of profound and often unsettling risks. The dream of a fully autonomous spacecraft, capable of making its own complex decisions, millions of miles from home, is a beautiful and a powerful one. But it is also a dream that is haunted by the specter of a catastrophic and potentially unrecoverable failure. One of the primary risks, as we have discussed, is the inherent brittleness and the unpredictability of many of our current AI systems. A deep learning model, for all its power, is essentially a complex statistical engine. It does not have a deep causal understanding of the world, and this can lead it to make strange and sometimes dangerous errors when it is confronted with a situation that is outside of its training data. A small and seemingly insignificant change in the input, a strange lighting condition, a faulty sensor reading, a rare geological formation can sometimes cause the AI to make a decision that is not just wrong, but catastrophically so. The risk of a runaway or an unintended behavior is a major concern, An AI that is designed to optimize a particular objective function to maximize the scientific data it collects, for example, could, in its single-minded pursuit of that goal, take an action that has a negative and unforeseen side effect, like depleting a critical resource or putting the spacecraft in a dangerous configuration. This is the classic AI safety problem of value alignment. The challenge of ensuring that the goals we program into our AI systems are truly aligned with our own, deeper, and often more nuanced, human values. The risk of data bias is another, insidious, and often difficult to detect threat. If the data that an AI is trained on is biased, then the AI's decisions will be biased as well. An autonomous rover that is trained on a dataset of terrestrial geology might systematically overlook a type of rock formation on Mars that is of great scientific interest, simply because it has no precedent in its training data. An AI that is used to select scientific targets could, if not carefully designed, develop a kind of confirmation bias, preferentially selecting the targets that are most likely to confirm our existing theories and systematically ignoring the anomalies that could lead to a new and revolutionary discovery. The lack of transparency in many of our AI systems, the black box problem, is another major risk. In a crisis, if an AI is making a series of decisions that are not understood by the human operators, it can lead to a loss of trust, to confusion, and to a delayed or an incorrect human intervention. The ability to interrogate an AI, to understand its reasoning, is not just a matter of intellectual curiosity. It is a critical operational necessity. And finally, there is the risk of a malicious cybersecurity attack. An autonomous spacecraft, with its complex and highly connected software systems, is a potential target for a sophisticated adversary. A hacker who could gain control of a spacecraft's AI could, in theory, use it to cause a great deal of damage, either by crashing the spacecraft, by using it to spy on another nation's assets, or by simply disrupting a critical scientific mission. The management of these risks is a new and essential discipline in the field of systems engineering. It requires a new and more holistic approach to safety, one that goes beyond the traditional hardware-focused models of reliability and that embraces the more complex and often more subtle failure modes of intelligent and adaptive software systems. It is a challenge that requires not just technical skill, but also a deep and humble awareness of the immense power and the potential peril of the new artificial minds that we are creating. The challenge of mitigating the biases that can be encoded in our AI algorithms is one of the most important and most difficult ethical and technical challenges in the field of artificial intelligence today. An AI model is a product of its training data, and if that data reflects the biases, the prejudices, and the blind spots of the society that created it, then the AI will learn and will perpetuate those biases. This is a problem that has been well documented in a number of terrestrial applications of AI, from biased hiring algorithms to racially discriminatory criminal justice systems. And it is a problem that we must be acutely aware of as we begin to deploy AI in the high-stakes and scientifically critical context of space exploration. The first and most important step in addressing this challenge is to be intentional and to be rigorous in the curation of our training data. The data must be as diverse, as representative, and as unbiased as possible. For an AI that is designed to classify galaxy, for example, the training data must include a wide range of different galaxy types from different cosmic epochs and observed with different instruments. If the training data is biased towards a particular type of galaxy, the AI will become an expert on that type, but it may perform poorly when it is presented with a more unusual or a more exotic object. The process of labeling the training data is another critical source of potential bias. If the labels are provided by a small and homogeneous group of human experts, then their own unconscious biases can be encoded into the AI's model. The use of a diverse and well-trained group of labelers and the use of techniques like blind labeling, where the labeler does not know the hypothesis being tested, can help to mitigate this risk. Another important strategy is the development of new AI techniques that are specifically designed to detect and to mitigate bias. There are now algorithms that can analyze a trained model and can identify the features that are most influential in its decisions. This can help to reveal whether the model is relying on a spurious or a biased correlation in the data. And there are new, fairness-aware machine learning algorithms that can be trained not just to maximize their accuracy, but to also minimize their reliance on certain protected attributes, like race or gender. The principle of transparency or explainability is also crucial. An AI that can explain its reasoning is an AI whose biases can be more easily identified and corrected. If a rover's AI decides to ignore a particular rock, the science team needs to be able to ask it, "Why did you ignore that rock?" and to get an answer that allows them to assess whether the AI's decision was a scientifically valid one, or whether it was the result of a bias in its training. And finally, we must have a culture of constant and critical evaluation. The deployment of an AI system is not a fire-and-forget process. The system's performance must be continuously monitored, its decisions must be audited, and it must be regularly retrained with new and more diverse data. The challenge of building a fair and an unbiased AI is a profound one. It is a challenge that forces us to confront the biases that are present in our own human societies and in our own human minds. And it is a challenge that requires a new and more conscious and more ethical approach to the design and the deployment of our most powerful new technologies. The goal is not just to build an AI that is intelligent. It is to build an AI that is wise. The security of the artificial intelligence systems that will be at the heart of our future space missions is a matter of critical and growing importance as our spacecraft become more autonomous and more connected and more reliant on complex software. They also become a more attractive and a more vulnerable target for a malicious cyber attack. The consequences of a successful attack on a deep space AI-powered mission could be catastrophic, ranging from the loss of a multi-billion-dollar national asset to the compromise of sensitive scientific data, to, in a worst-case scenario, the loss of a human crew. The challenge of securing these systems is a multi-layered one. It begins with the development of a secure software development lifecycle. The AI's code must be written with security in mind from the very beginning. This includes the use of secure coding practices, of rigorous code reviews, and of automated, static, and dynamic security testing tools. The goal is to find and to fix the vulnerabilities in the code before the spacecraft ever leaves the ground. Another crucial layer of defense is the protection of the AI's training data and its trained model. The integrity of a machine learning model is completely dependent on the integrity of the data it was trained on. A sophisticated adversary could, in theory, attempt to poison the training data, to subtly manipulate it in a way that would cause the AI to learn a malicious or an incorrect behavior. The protection of the training data pipeline and the use of cryptographic techniques to ensure the integrity of the trained model itself are essential security measures. Once the spacecraft is in space, the communication link to the ground is a major potential vulnerability. All the commands that are sent to the spacecraft and all the data that is sent back must be protected with strong end-to-end encryption. And the ground systems themselves, the mission control centers and the deep space network must be protected with a robust and a multi-layered cybersecurity defense. But even with the best protections, we must assume that an adversary might, one day, be able to breach these outer defenses. And so, we must also have a layer of onboard security. The spacecraft's computer systems must be designed with the principle of least privilege, where each component of the software has only the permissions it needs to do its job. And there must be a system of intrusion detection and of autonomous response. The AI itself can be a powerful tool in this regard. An AI could be trained to recognize the normal behavior of the spacecraft systems, and it could be used to detect any anomalous or suspicious activity that could be a sign of a cyber attack. And in the event of a detected attack, the AI could autonomously take action to isolate the compromised component, to switch to a backup system, and to alert the human operators on the ground. The security of our AI systems in space is not just a technical problem, it is also a geopolitical one. The development of international norms, of treaties, of rules of the road for the responsible and the peaceful use of AI in space is a crucial and an urgent diplomatic task. We must work together as a global community to ensure that space remains a domain of peaceful exploration and of scientific collaboration, and that it does not become a new and a dangerous theater for cyber warfare. The governance of our activities in space, and particularly the use of powerful new technologies like artificial intelligence, is a complex and evolving challenge, one that requires a delicate balance between the promotion of innovation, the assurance of safety, and the protection of the long-term common interests of all of humanity. The legal and regulatory framework for space activities is a patchwork of international treaties, of national laws, and of informal, soft law guidelines. The cornerstone of this framework is the 1967 Outer Space Treaty, a remarkable document that was forged in the midst of the Cold War. The treaty establishes some of the most fundamental principles of space law. It declares that outer space, including the moon and other celestial bodies, is the province of all mankind, that it is free for exploration and use by all states, and that it is not subject to national appropriation by claim of sovereignty. It also prohibits the placement of weapons of mass destruction in orbit or on celestial bodies, and it establishes that states are responsible for the activities of their governmental and their non-governmental entities in space. This treaty, and the other related UN space treaties that followed, have provided a remarkably stable and effective framework for the peaceful and the cooperative exploration of space for over half a century. But the world of space has changed dramatically since the 1960s. The rise of the commercial space industry, the prospect of space resource utilization, the problem of orbital debris, and the development of new and potentially disruptive technologies like AI are all posing new challenges to this existing legal framework. The governance of AI in space is a particularly complex and pressing issue. There are, at present, no specific international treaties that deal with the use of AI in space. The existing framework is largely based on the general principle that states are responsible for their national activities in space, and this responsibility extends to the activities of the AI systems they deploy. But as our AI systems become more autonomous, and as their decision-making processes become more opaque, the question of how to assign responsibility and accountability in the event of a failure or of a harmful action becomes increasingly difficult. This has led to a growing international dialogue about the need for a new set of ethical and regulatory guidelines for the development and the deployment of AI in space. This dialogue is taking place in a variety of fora, from the UN Committee on the Peaceful Uses of Outer Space to a host of other international and non-governmental organizations. The goal is to develop a set of shared best practices and norms of behavior that can guide the responsible development of AI in space. These could include principles like transparency, where the decision-making processes of an AI should be, to the greatest extent possible, understandable and explainable. It could include the principle of meaningful human control, the idea that for any life-critical decision, A human being should always be in the loop. And it could include the principle of benefit sharing, the idea that the immense benefits of space exploration and of AI technology should be shared as widely as possible. For the good of all of humanity, the governance of AI in space is not about stifling innovation with a heavy-handed, top-down regulation. It is about creating a clear, predictable, and ethical framework that can foster a culture of safety, of responsibility, and of peaceful collaboration. A framework that will allow us to unlock the immense potential of this powerful new technology, while at the same time protecting the long-term and very precious future of our shared human adventure in the cosmos. The ethical use of artificial intelligence in the vast and often contested frontier of space is a challenge that cannot be solved by any single nation alone. It is a challenge that requires a deep and a sustained international cooperation. The development of a shared global consensus on the ethical principles that should guide our use of AI in space is essential for ensuring that this powerful and new technology is a force for peace, for collaboration, and for the benefit of all of humanity. The reasons for this are both practical and philosophical. On a practical level, space is an inherently global domain. The satellites that provide our global communication, our navigation, our weather forecasting, are a shared international resource. The problem of orbital debris is a global problem, as a single piece of debris can threaten the satellites of all nations. And the scientific exploration of the cosmos is a fundamentally international endeavor, with a long and a proud history of collaboration between different space agencies and scientific communities. The use of AI in this shared domain must, therefore, be governed by a shared set of rules. A lack of international agreement on issues like the use of AI for satellite rendezvous and proximity operations, for example, could lead to a dangerous and a destabilizing Wild West in orbit, with an increased risk of misunderstanding, of miscalculation, and of conflict. On a deeper philosophical level, the exploration of space is an endeavor that speaks to our shared human identity. When we look up at the stars, we are not just looking out at a physical universe. We are also looking in at our own human desire to understand, to explore, and to transcend our own terrestrial limits. The ethical framework that we develop for our activities in space should reflect this shared humanistic vision. It should be a framework that is based on the principles of peace, of cooperation, of environmental stewardship, and of a commitment to using the knowledge and the resources of space for the benefit of all people on Earth. The development of this shared ethical framework is a task that is already underway. The United Nations Committee on the Peaceful Uses of Outer Space is the primary international forum for this dialogue, through its legal subcommittee and its scientific and technical subcommittee. COPUOS is providing a space for the nations of the world to come together, to share their perspectives, and to work towards a consensus on the complex, legal, and ethical issues that are being raised by the new space technologies. This is often a slow and a painstaking diplomatic process, but it is a crucial one. And it is a process that is not just happening at the governmental level. There is also a vibrant and a growing global community of non-governmental organizations, of academic institutions, of industry associations that are all contributing to this important dialogue. The challenge of building a global ethical consensus on the use of AI in space is a profound one. It is a challenge that will require a new level of international cooperation, of mutual trust, and of a shared, long-term vision. But it is a challenge that we must rise to, the future of our journey into the cosmos, and perhaps the future of our own human society may depend on it. As we stand on the cusp of a new era of exploration, An era where artificial intelligence will be an indispensable partner in our journey to the stars. We are confronted by a series of deep and profound questions, questions that are not just about science and technology, but about our very nature as a species, the quest to understand the origin of the universe, to search for life beyond Earth, to push the boundaries of our knowledge and of our presence in the cosmos, is a quest that is, in the end, a quest to understand ourselves. The universe that modern cosmology has revealed to us is one of almost unimaginable scale, of breathtaking beauty, and of deep, and often unsettling, mystery. It is a universe that was born from the quantum fluctuations of a primordial void, a universe that is expanding at an accelerating rate, driven by a mysterious, dark energy. A universe that may be just one of an infinite number of other parallel realities. And it is a universe that seems to be, in some deep and fundamental way, finely tuned for the existence of beings like us. Beings who can look up at the sky and wonder. The technologies that we are creating to explore this universe, and in particular, the new and powerful technologies of artificial intelligence, are a testament to the remarkable and perhaps unique power of the human mind. They are a reflection of our own innate curiosity, of our own creative ingenuity, of our own relentless desire to understand. But these new technologies also present us with a new set of profound challenges and of deep ethical responsibilities. As we create these new artificial minds, we must be wise and we must be humble. We must ensure that they are aligned with our own deepest human values. We must build a future that is not a competition between human and artificial intelligence, but a deep and synergistic partnership. The journey ahead is a long and a challenging one. There will be setbacks, there will be failures, there will be moments of profound doubt, but the human spirit has always been an exploratory one. We are a species that is not content to stay within the familiar confines of our own small world. We are a species that is driven to look over the next hill, to cross the next ocean, to climb the next mountain. And now, the next mountain is Mars, and the next ocean is the vast and beautiful emptiness of interplanetary space. The quest to understand the origin of the universe and our own place within it is a quest that may never have a final, complete answer. It is a journey, not a destination, and it is a journey that is, in itself, a source of deep meaning and of profound human purpose. And as you lie in the quiet of the night, as your own individual consciousness prepares to embark on its own nightly journey into the mysterious and often cosmic landscape of your dreams, you can feel a sense of participation in this grand and beautiful and deeply human adventure. The grass is green, or so it seems. In the reality you perceive, the blades of grass in a sunlit field reflect a particular wavelength of light, and the three types of color receptors in your eyes, working in concert with the intricate neural architecture of your brain, interpret this signal as green. But this is not the color of the grass itself. To a dog with only two types of color receptors, that same field of grass appears yellowish-gray. To a bee, which can see in the ultraviolet spectrum, the grass is part of a complex, multicolored tapestry of patterns that are completely invisible to us. So, what is the true color of the grass? The question itself is flawed. Color is not a property of the object. It is a perception, a subjective experience created in the mind of the observer. Before you look at it, the grass is not green, nor is it beige. It simply is. A complex molecular structure that reflects a spectrum of electromagnetic radiation. The same is true for the rest of the world. The ground beneath your feet feels solid, unyielding. But if you were to zoom in, to journey down into the subatomic realm of the atoms that make up the floor, you would find that it is, in fact, almost entirely empty space. The nucleus of an atom is a tiny, dense point, and the electrons that orbit it are even smaller, separated by vast, cosmic-scale voids. The solidity you feel is not a property of the matter itself. It is an illusion, a powerful and convincing one, created by the repulsive force of the electrical fields of the atoms in your body pushing against the electrical fields of the atoms in the floor. You are not physically touching the floor. You are energy, interacting with energy. The screen you are looking at right now, the sound of my voice in your ears, the feeling of the chair supporting your body, all of these are, at their core, just electrical signals, complex patterns of information being processed and interpreted by your brain. Your brain has never seen the light from the screen. It has never heard the sound waves from the speaker. It has never touched the fabric of the chair. It has only ever known the language of electrical impulses, the silent electrochemical chatter of its own internal world. The reality you are experiencing right now is a high-resolution, multi-sensory, and perfectly rendered simulation. A world picture that has been constructed for you, by you, in the dark, silent theater of your own mind. So, if everything you have ever seen, ever felt, ever thought, is a mental construction, a story that your brain is telling itself, then what is the difference between this waking reality and the reality of a dream? Are you dreaming with your eyes open, or are you truly awake? Imagine you are standing in a large, open field, and you and a friend are holding opposite ends of a long, taut rope. You can feel the tension in the rope, a direct, physical connection that spans the distance between you. Every subtle tug, every gentle release that your friend makes at their end is transmitted through the rope and is felt by you, almost instantaneously. This is our classical, intuitive understanding of how the world works. It is a world of locality, a world where things can only influence each other through direct, physical contact or through a clear, unbroken chain of cause and effect. A push causes an object to move. A sound wave travels through the air. A signal is transmitted along a wire. This is the world of Isaac Newton, a world that is orderly, predictable, and grounded in common sense. But now, imagine something far stranger. You and your friend drop the rope. There is nothing between you but the empty air. And yet, when your friend makes a tugging motion, you instantly feel a pull in your own hands. There is no rope, no string, no visible connection of any kind. Your friend could be on the other side of the field or on the other side of the planet, and the effect would be the same, instantaneous. This is a world that defies our classical intuition. It is a world that is non-local. And it is a world that, according to the strange and beautiful laws of quantum mechanics, is the true underlying reality of our universe. At the smallest, most fundamental scales of existence, particles can become entangled, linked in a way that transcends the normal boundaries of space and time. This is not like a wireless signal from your phone, which travels at the speed of light and can be detected and traced. This is a deeper, more mysterious connection, a spooky action at a distance. As a skeptical Albert Einstein famously called it, if you take a single atom and you split it into two entangled parts and you send these two parts to opposite ends of the earth, you will find that a measurement on one part will instantly influence the state of the other. There is no signal, no delay, no physical link of any kind. It is as if the two particles are not two separate things, but are two aspects of a single, unified, and non-local reality. It is as if separation itself is an illusion. And if the universe behaves in this strange, non-local way at its very core, then what does that say about the macroscopic world of our own experience? Is the solid, separate, and seemingly local world we see around us just a shadow, a projection of a much deeper, more unified, and more mysterious reality? Is it possible that all the matter and all the energy in the universe, the distant stars and the atoms in your own body, are all part of a single, vast, and interconnected quantum system? This profound and unsettling idea that the universe may not be what it seems, that the very fabric of our reality may be an illusion, is a concept that has begun to migrate from the fringes of theoretical physics and philosophy into the heart of mainstream scientific inquiry. If the separation between objects is not as real as it appears, if the universe is, at its core, a holistic and non-local entity, then what is the true nature of this underlying, unified reality? One of the most radical and yet scientifically plausible of these ideas is the holographic principle. This is a concept that emerged from the deep theoretical study of black holes, and it suggests that all the information contained within a three-dimensional volume of space can be, in a sense, encoded on its two-dimensional boundary. It is as if our entire three-dimensional universe is a kind of hologram, a complex three-dimensional projection of information that is stored on a distant two-dimensional surface at the edge of the cosmos. In this picture, the world of our experience, with its depth, its solidity, its separation of objects in space, is not the fundamental reality. It is an emergent, and in some sense, illusory, phenomenon, a holographic image generated from a deeper, more fundamental, and non-local informational reality. Another, and perhaps even more unsettling, possibility is the simulation hypothesis. This is the idea that our entire universe, with all its history, all its laws, and all its inhabitants, is a sophisticated computer simulation, a virtual reality created by a far more advanced, post-human civilization. The laws of physics are not fundamental truths of nature. They are the programmed rules of the simulation. The particles that make up our world are not solid, physical things. They are pixels on a cosmic screen. And our own consciousness, our thoughts, our feelings, our very sense of self, may be nothing more than the product of a complex, artificial intelligence running on a vast, and as yet unimaginable, computational substrate. This is an idea that can feel like a dizzying, philosophical vertigo. And yet, it is an idea that is being taken seriously by a growing number of physicists and philosophers, as it provides a potential explanation for a number of the strange and seemingly fine-tuned features of our own universe. The fact that the universe seems to be governed by a set of elegant mathematical laws, the fact that there seem to be fundamental, discrete units of space, time, and energy at the Planck scale. The strange, observer-dependent nature of quantum reality, all of these are features that would be natural, and even expected, in a simulated reality. The universe, in this view, is a grand and beautiful video game, and we are, perhaps, just non-player characters, with no knowledge of the game's creators, or of the true, base reality that lies outside the simulation. Or perhaps, our universe is part of an even grander and more complex structure, a multiverse. The theory of eternal cosmic inflation suggests that our universe may be just one bubble in an infinite, self-reproducing cosmic foam of other universes, each with its own, potentially different, physical laws. The many worlds interpretation of quantum mechanics suggests that every quantum event splits the universe into a branching tree of parallel realities. In this vast, and perhaps infinite, multiverse, every possibility is realized. There are an infinite number of versions of you, living out an infinite number of different lives. In this picture, our sense of a single, unique reality is an illusion born of our limited perspective, our confinement to a single branch of the universal wave function. We feel separate, but we are, in fact, part of a much larger and much stranger whole. All of these ideas, the hologram, the simulation, the multiverse are, for now, on the speculative frontiers of science, but they are all pointing in the same profound direction. They are all suggesting that the universe we perceive with our senses, the world of separate, solid, and local objects, is not the ultimate reality. It is a shadow, a projection, a single frame in a much larger and much more mysterious cosmic movie. And the true nature of that movie, the source of its light, the identity of its director, remains the deepest and most beautiful of all scientific questions. The story of our modern scientific grapple with the nature of reality begins, in many ways, with a single, seminal, and deeply reluctant paper. In 1935, Albert Einstein, along with his two younger colleagues, Boris Podolsky and Nathan Rosen, published a paper that was intended to be a death blow to the strange and unsettling new theory of quantum mechanics. They titled it, with a characteristically academic and understated flair, "Can quantum mechanical description of physical reality be considered complete?" But the question it posed, and the thought experiment it contained, would ignite a debate that would rage for decades and would ultimately lead to a profound and revolutionary transformation in our understanding of the universe. Einstein, by this time, was the elder statesman of physics, a global icon who had single-handedly overthrown the Newtonian universe with his theories of relativity. And the universe he had revealed was a beautiful, elegant, and deeply orderly one. It was a grand cosmic clockwork, a universe of smooth, curved space-time, of deterministic laws, of a reality that was objective, independent, and, in a word, real. But quantum mechanics, the new theory that had been developed by a younger generation of physicists, was a direct affront to this classical common-sense worldview. It was a theory that was built on a foundation of randomness or of probability, of uncertainty. It suggested that a particle could be in many places at once, that its properties were not defined until they were measured, that the universe, at its core, was a game of cosmic dice. And Einstein, famously, did not believe that God played dice. For centuries, the worldview of physics had been that of local realism. It was a worldview with two simple and deeply intuitive pillars. The first was locality, the idea that an object can only be influenced by its immediate surroundings. An action here cannot have an instantaneous effect on something over there. All influences, all information must travel through space at a finite speed, a speed that is limited by the speed of light. This was a cornerstone of Einstein's own theory of special relativity. If you are a NASA engineer and you want to send a command to the Mars rover, you must wait at least 3 minutes for your signal to travel across the intervening space. There is no way around this cosmic speed limit. The second pillar was realism, the belief that the objects of the physical world have definite, objective properties. Whether we are observing them or not, a rock is a rock. It has a definite position, a definite mass, a definite shape. The moon, as Einstein was fond of saying, is still there, even when nobody is looking at it. This belief in an objective, observer-independent reality was the very foundation of the scientific method. Together, these two principles, of locality and realism, formed a sturdy and reassuring framework for understanding the world. They were the bedrock of the classical physics of Newton and Maxwell, a physics that had been so spectacularly successful in explaining everything from the fall of an apple to the motion of the planets. It was a picture of a predictable, rational, and transparent cosmos. And then, in the early 20th century, as scientists began to probe the strange new world of the atom, this beautiful classical picture began to unravel. The unraveling began with a series of experiments that revealed a world that was not just strange, but seemingly paradoxical. The classical picture of matter was that of tiny, solid, billiard ball-like particles. But when scientists performed the double-slit experiment, they found that a single electron, when not observed, behaves like a wave, passing through both slits at once and interfering with itself. The very nature of the electron's reality seemed to depend on the context of the experiment, on the question that was being asked of it. This was the wave-particle duality, the central, and still mysterious, paradox of the quantum world. But even stranger was the implication that the act of observation itself seemed to play a crucial and creative role in shaping reality. It was as if the electron's properties were not defined, were not real until they were measured. This was a direct challenge to the principle of realism. And then came the phenomenon of entanglement, a direct challenge to the principle of locality. The theory of quantum mechanics predicted that two particles could become linked in such a way that their properties would remain correlated, no matter how far apart they were separated. A measurement on one particle would have an instantaneous effect on the other, a spooky action at a distance that seemed to violate the cosmic speed limit. To Einstein, this was a clear sign that the theory was incomplete. There had to be a deeper, more classical reality hiding beneath the probabilistic and seemingly non-local facade of quantum mechanics. There had to be hidden variables, unknown properties of the particles that were determined at the moment of their creation, and that carried with them the instructions for how to behave when they were later measured. This would restore both realism and locality. The famous EPR paper of 1935 was the most sophisticated and powerful articulation of this argument. It was a thought experiment and Gedankenexperiment designed to expose the absurdity and the incompleteness of the quantum mechanical worldview. It imagined a pair of entangled particles, created at a central source and sent flying off in opposite directions. By measuring the position of one particle, you could, with perfect certainty, predict the position of the other, without in any way disturbing it. And by measuring the momentum of the first particle, you could predict the momentum of the other, since you could, in principle, know both the precise position and the precise momentum of the second particle. Both of these properties must be simultaneously real. But this directly contradicted another of the strange principles of quantum mechanics, Heisenberg's uncertainty principle, which states that it is impossible to know both the position and the momentum of a particle with perfect precision at the same time. The conclusion, for EPR, was inescapable. Quantum mechanics must be an incomplete theory. It was just a statistical approximation of a deeper, more fundamental, and locally realistic reality. But Niels Bohr, the great Danish physicist and the philosophical father of the quantum revolution, disagreed profoundly. He argued that the EPR paper was based on a fundamental misunderstanding of the nature of quantum reality. For Bohr, a quantum system, like an entangled pair of particles, is an indivisible whole. You cannot speak of the properties of one particle independently of the other, or independently of the measuring device that you use to observe them. Reality is not a collection of separate, independent things with pre-existing properties. It is a holistic, contextual, and relational phenomenon. The properties of a particle are not revealed by a measurement. They are created in the act of measurement. The debate between Einstein and Bohr was one of the great intellectual duels of the 20th century. It was a clash of two, fundamentally different, and seemingly irreconcilable worldviews, and for decades, it remained a purely philosophical debate, a matter of taste and interpretation. there seemed to be no way to experimentally distinguish between the two pictures. And then, in the 1960s, a quiet, unassuming, and brilliant physicist named John Stuart Bell, working in his spare time at the CERN laboratory in Geneva, found a way. John Bell was not a man who was looking for a revolution. He was a particle physicist, a man who was grounded in the practical and often messy world of building and understanding particle accelerators. But in the quiet of his own mind, he was haunted by the deep, unresolved, and philosophical questions that lay at the heart of quantum mechanics. He was particularly intrigued by the work of the American physicist David Bohm, one of the few who had taken Einstein's skepticism seriously and had developed a fully fledged hidden variable theory, a theory that could reproduce all the predictions of standard quantum mechanics, but which was built on a foundation of a deeper, deterministic, and non-local reality. Bohm's theory was largely ignored by the mainstream physics community, but for Bell, it was a proof of principle. It showed that hidden variable theories were not just a philosophical fancy, they were a real mathematical possibility. This planted a seed in Bell's mind. Was there a way to experimentally test the very idea of local realism itself? Was there a way to devise an experiment that would give one result if Einstein's classical common-sense worldview was correct, and a different result if the strange, non-local, and probabilistic world of quantum mechanics was the true reality? After months of intense and often solitary work, Bell found the answer. His insight was a stroke of pure genius. He realized that while a simple experiment with a single pair of entangled particles could not distinguish between the two worldviews, a series of experiments, with the detectors set at different and randomly chosen angles, could. He derived a now famous mathematical inequality. Bell's inequality, which set a strict upper limit on the amount of statistical correlation that could be observed between the measurements on the two separated particles. If the world was governed by the principles of local realism, quantum mechanics, on the other hand, predicted that for certain specific settings of the detectors, this inequality would be violated. The correlations would be stronger than any local realistic theory could possibly explain. Bell had, in a single, beautiful, and profound paper, transformed the Einstein-Bohr debate from a matter of philosophy into a matter of experimental, empirical fact. The universe had to make a choice. It could be local and realistic, in which case Bell's inequality would be obeyed, or it could be quantum mechanical, in which case the inequality would be violated. It could not be both. To understand the essence of Bell's theorem, imagine a game. You have two separated players, Alice and Bob. A central source sends each of them a particle from an entangled pair. Alice and Bob can each choose to measure their particle in one of two different ways. Say, by passing it through a polarizer that is oriented either vertically or horizontally. After they have made their measurements, they get together and compare their results. Bell's inequality is a statement about the statistical correlations between their results, averaged over many runs of the experiment. If the particles are like classical objects, with predetermined, hidden properties, then there is a limit to how strongly their results can be correlated. But if they are quantum mechanical, if they are part of a single, non-local, entangled state, then their results can be more strongly correlated than any classical theory would allow. It is as if they are part of a team that is so perfectly coordinated that they can win the game more often than the classical rules would permit. Bell's work, when it was published in 1964, was initially met with a deafening silence. The technology to actually perform such a delicate and precise experiment did not yet exist, and the mainstream physics community, for the most part, had accepted the pragmatic Copenhagen interpretation and had moved on from what they saw as the sterile philosophical debates of the founding generation but the seed had been planted. And in the early 1970s, a young and stubbornly independent-minded graduate student at Columbia University named John Clauser stumbled upon Bell's paper and decided that he was going to be the one to put it to the test. John Clauser was a man who was not afraid to challenge the orthodoxy. While his professors and his peers were focused on the more fashionable and well-funded frontiers of particle physics, Clauser was drawn to the deep, foundational, and often overlooked questions that lay at the heart of quantum mechanics. When he read Bell's paper, he saw not just a theoretical curiosity, but a profound experimental challenge. He wrote to Bell, and their correspondence solidified his resolve. He was going to build an experiment to test Bell's inequality. Together with his student, Stuart Friedman, Clauser designed and built the first practical experimental test of Bell's theorem. The experiment, conducted at the University of California, Berkeley, in 1972, was a masterpiece of shoestring ingenuity and experimental grit. It involved creating pairs of entangled photons by exciting calcium atoms and then measuring the correlations in their polarization as they flew off in opposite directions. The setup was delicate, the signals were weak, and the technical challenges were immense. But after months of painstaking work, they had their result. The data was clear, and it was unambiguous. Bell's inequality was violated. The correlations between the photons were stronger than any local realistic theory could explain. The predictions of quantum mechanics were correct. Einstein, it seemed, was wrong. The universe was, in some deep and fundamental way, non-local. This was a groundbreaking result, a landmark in the history of physics, but it was not the final word. Clauser's experiment, as brilliant as it was, had several potential loopholes, subtle and sometimes contrived, ways in which a determined, local realist could still explain the result. The locality loophole, for example, was the possibility that the two detectors, or the choice of their settings, could have somehow communicated with each other during the experiment, at a speed less than or equal to the speed of light, to coordinate their results. The detection loophole was the fact that the photon detectors were not perfectly efficient. They missed many of the photons. It was possible, in principle, that the detectors were only detecting a biased and unrepresentative subsample of the photons, the ones that just happened to be correlated in a quantum mechanical way. It was the French physicist Alain Aspect who, in the early 1980s, took on the challenge of closing the locality loophole. Working at the Institute of Optics in Orsay, France, Aspect and his team designed a series of increasingly sophisticated and elegant experiments. Their key innovation was the use of a high-speed acousto-optical switch that could change the orientation of the polarizers while the photons were in flight, after they had already left the source. The choice of which measurement to perform on each photon was made so quickly and so late that there was simply not enough time for any signal, traveling at the speed of light, to communicate that choice to the other side of the experiment before the other measurement was completed. The two measurement events were space-like separated, in the language of relativity, meaning they were causally disconnected. The results of Aspect's experiments were a stunning confirmation of Clauser's earlier work. Bell's inequality was violated, and by an even greater margin. The locality loophole was, for all practical purposes, closed. The spooky action at a distance was real, but the work was still not done. There were other, more subtle, loopholes to close. And it was the Austrian physicist Anton Zeilinger who, in the 1990s and 2000s, would take the experimental tests of Bell's theorem to a new level of rigor, of scale, and of conceptual beauty. Zeilinger is a master of experimental quantum optics, a physicist with a deep philosophical bent and a flair for the dramatic. One of his team's most famous experiments, conducted in 2007, was a Bell test that was performed not in a laboratory, but across the open air between two of the Canary Islands, La Palma and Tenerife, a distance of 144 kilometers. This was a feat of immense technical difficulty, requiring the precise alignment of telescopes and the transmission of single, entangled photons through the turbulent atmosphere. The sheer scale of the experiment was a powerful and visceral demonstration of the reality of non-locality. But Zeilinger's most profound contribution was his ingenious solution to the freedom of choice loophole. This is the most philosophical of all the loopholes, the last refuge of the determined local realist. It is the idea that the choice of which measurement to perform is not truly free or random, but is itself determined by some hidden common cause in the shared past of the experiment, a cause that also determines the properties of the entangled particles. It is a form of superdeterminism, a grand conspiracy of nature that perfectly mimics the predictions of quantum mechanics. To close this loophole, you need a source of randomness that is so ancient, so distant, and so causally disconnected from the experiment that it could not possibly be part of such a conspiracy. And Zeilinger found the perfect source: distant quasars. In an experiment conducted in 2018, his team used the light from two ancient quasars on opposite sides of the sky, whose light had been traveling towards the Earth for billions of years, to control the settings of their polarizers in a Bell test. The choice of whether to measure the polarization of a photon vertically or horizontally was determined, in real time, by whether the incoming light from a quasar was red or blue. Any hidden variable that was trying to coordinate this experiment would have had to set its plan in motion billions of years ago, long before the Earth, or even our solar system, had formed. The results, once again, were a perfect confirmation of quantum mechanics. The freedom of choice loophole was closed. The last desperate argument for local realism was laid to rest. In 2022, the Nobel Prize in Physics was jointly awarded to John Clauser, Alain Aspect, and Anton Zeilinger for their pioneering and collectively definitive experimental work on quantum entanglement. The prize was a long overdue recognition of a series of experiments that have not just confirmed one of the strangest predictions of a scientific theory, but have fundamentally and irrevocably changed our very understanding of the nature of physical reality. The universe is not local, and it is not, in the classical sense, real. The world of our everyday, common sense intuition is an illusion, a macroscopic approximation of a much deeper, much stranger, and much more beautifully interconnected quantum reality. The definitive, experimental confirmation of quantum non-locality, the reality of spooky action at a distance, is a discovery of such profound and mind-altering significance that we are still, as a scientific and philosophical culture, struggling to fully grasp its implications. It is a discovery that shatters the very foundations of our classical, mechanistic worldview and forces us to confront a universe that is far more holistic, more interconnected, and more mysterious than we ever imagined. If the principle of locality is false, if an action here can have an instantaneous effect on something over there, without any signal passing through the intervening space, then our very concept of space as the medium that separates and insulates objects is called into question. Space, it seems, does not separate entangled particles. It is simply the arena in which their pre-existing non-local connection is manifested. This suggests that there may be a deeper level of reality, a subspace or a pre-space, that is not governed by the familiar geometry of our three-dimensional world, a level of reality where everything is, in a sense, in immediate contact with everything else. This is the idea of a holographic universe, a concept that, as we have seen, has its roots in the physics of black holes. It is the idea that our familiar three-dimensional world is a kind of projection, a holographic image of information that is stored on a distant two-dimensional surface. In this picture, the non-locality of entanglement is no longer a mystery. The two entangled particles are not really separated by a vast distance in three-dimensional space. They are at the deeper informational level of the hologram surface, right next to each other. Their instantaneous connection is just a reflection of their proximity on the underlying holographic plate. This is a radical and deeply counterintuitive idea, but it is one that is being taken very seriously by many of the world's leading theoretical physicists, as it offers a potential path towards a unified theory of quantum gravity. The failure of realism, the fact that a particle's properties are not defined until they are measured, is equally profound. It suggests that the universe, at its core, is not a world of things, but a world of information. This is the essence of John Wheeler's it from bit hypothesis. The physical reality of a particle, its itness, arises from the informational bitness of a series of yes-no questions that are answered in the act of measurement. A particle is not a solid, pre-existing object. It is the outcome of a cosmic computation. This informational view of reality provides a natural framework for understanding the universe as a vast quantum computer. The laws of physics are the software, the rules that govern how the information is processed. The quantum fields that fill all of space are the hardware, the computational substrate, and the evolution of the universe is the running of a grand cosmic program. This, in turn, leads us to the most unsettling, and yet strangely logical, of all possibilities, the simulation hypothesis. If the universe is, at its core, informational and computational, then is it not possible, and perhaps even probable, that our entire reality is a simulation, a virtual world created by a far more advanced intelligence? The philosophical implications of this new, non-local and informational worldview are immense. It challenges our deep-seated sense of individuality and separation. If the universe is a single, entangled, holographic, and informational whole, then the boundaries between ourselves and the world, between mind and matter, between the observer and the observed, are not as solid as they appear. We are not separate, isolated beings, looking out at an external world. We are an integral and participatory, part of a single, vast, and co-creative cosmic process. Our consciousness is not just a passive witness. It is an active participant in the ongoing creation of reality. The discoveries of Bell, of Clauser, of Aspect, and of Zeilinger have not just given us a new picture of the universe. They have given us a new picture of ourselves. They have shown us that the world of our everyday, classical intuition is a beautiful and useful illusion, a user-friendly interface that hides a much deeper, much stranger, and much more beautifully interconnected quantum reality. And the great adventure of 21st century science is to continue to peel back the layers of this illusion, to explore the depths of this hidden reality, and to learn to live in a way that is worthy of the profound, mysterious, and deeply magical universe we are now beginning, for the very first time, to truly see. The history of video games, from the simple black and white pixels of Pong to the breathtakingly photorealistic, ray-traced landscapes of today, is a story of an exponential and seemingly inexorable increase in computational power and graphical fidelity. In 1972, the peak of interactive entertainment was two: simple, digital paddles and a bouncing, square ball. 50 years later, a mere blink of an eye in the grand sweep of human history, we can now create and explore digital worlds that are, in many ways, indistinguishable from reality. We can walk the streets of a bustling, virtual city. We can fly through the clouds of a simulated sky. We can feel the sun on our skin and the wind in our hair in a fully immersive, virtual reality environment. The line between the real and the virtual is becoming increasingly blurred. And if this is the progress we have made in just half a century, what will be possible in 1,000 years? In 1,000,000? The logical endpoint of this trajectory is a future where simulated realities are not just indistinguishable from base reality, but are far more numerous. An advanced, post-human civilization, with access to a planetary, or even stellar, scale of computational resources, could, in principle, create a vast number of ancestor simulations, highly detailed and perfectly realistic. Simulations of their own evolutionary past, populated by artificial conscious beings who have no idea that they are living inside a computer program. This is the foundation of Nick Bostrom's famous simulation argument. It is not a proof that we are living in a simulation, but a powerful probabilistic argument that forces us to confront a startling trilemma. Bostrom argues that one of the following three propositions must be true. First, it is possible that almost all civilizations at our level of technological development go extinct before they reach the post-human stage, the stage where they have the computational capacity to run such simulations. This is the great filter hypothesis, the idea that there is some, almost insurmountable, hurdle that prevents the emergence of long-lived, technologically advanced civilizations. Second, it is possible that almost all post-human civilizations lose interest in running ancestor simulations. Perhaps they find it ethically problematic, or perhaps they have moved on to other, more interesting and less computationally expensive forms of entertainment or scientific inquiry. Or third, if the first two propositions are false, if a significant number of civilizations do survive to a post-human stage, and they do choose to run a large number of ancestor simulations, then the number of simulated beings, like us, would be vastly, astronomically larger than the number of real, non-simulated beings. And if that is the case, then a simple, statistical argument suggests that it is overwhelmingly probable that we are one of the simulated beings, not one of the real ones. The simulation hypothesis is a modern, scientific, and computational version of some of the oldest and most profound philosophical questions. It is Plato's cave, updated for the digital age. It is Descartes' evil demon, reimagined as a cosmic programmer. It is the Buddhist concept of Maya, the idea that the world of our sensory experience is a powerful and convincing illusion. But unlike its philosophical predecessors, the simulation hypothesis is not just a metaphysical speculation. It is a concept that is, in principle, testable. If our universe is a simulation, then it must be running on some kind of computational substrate, and that substrate must have a finite resolution, a finite processing speed. This could manifest itself in the very laws of our own physics, the existence of a smallest possible unit of length, the Planck length, and a smallest possible unit of time. The Planck time could be seen as the pixel size of the cosmic simulation. The fact that the universe seems to be governed by a set of elegant mathematical laws could be a sign that we are living in a world that has been coded. And the strange, observer-dependent nature of quantum reality, the fact that particles do not have definite properties until they are measured, is eerily similar to the way that a modern video game renders its graphics. The game engine does not calculate the state of the entire game world all at once. It only renders the parts of the world that the player is currently looking at, a form of lazy computation that saves on processing power. Perhaps the universe does the same. Perhaps the wave function collapse is the universe's rendering engine, creating reality on the fly as it is needed in response to the requests of our observations. The search for these glitches in the matrix, for the subtle, telltale signs of an underlying computational reality, is a new and exciting, if highly speculative, frontier of scientific inquiry. Physicists are looking for subtle violations of the symmetries of space-time, for patterns in the cosmic microwave background that might look like the raster scan of a cosmic television screen, for any hint that our reality is not as smooth, as continuous, and as real as it appears. Whether we will ever find such definitive proof is an open question. But the simulation argument itself is a powerful and valuable tool for thought. It forces us to question our most basic and unexamined assumptions about the nature of reality. It encourages us to maintain a stance of intellectual humility, to recognize that the world may be far stranger and far more complex than our current scientific and philosophical models can accommodate. And it raises a final, and perhaps unanswerable, set of questions. If we are living in a simulation, who are the simulators? What is their nature? What is their purpose in creating a universe like ours? Are we a scientific experiment, a work of art, a historical reenactment, or are we just a piece of entertainment? A very advanced and very immersive video game for beings whose intelligence and whose motives are forever beyond our comprehension. The silence of the cosmos, the great silence of the Fermi paradox, takes on a new and chilling meaning in this context. Perhaps the reason we have not heard from any other advanced civilizations is because they are all, like us, just characters in a simulation, with no way to communicate with the real world outside. Or perhaps, even more chillingly, our simulation is the only one that has been allowed to run this far. Perhaps the architects are watching and listening and waiting.